Cheers. Thanks. So like you're planning to do it with some sort of force or tactile sensing or proprioceptive then?
Yes, some proprioceptive sensing within the grip itself.
Yeah. Thanks.
Thank you. So the next question is from Ming Xuan.
Yeah, thank you. Can you hear me?
Yeah.
Yes.
I have one question. So, like in some easy case, like if the fruit is like most of the fruit is outside, can be seen by the camera. In that case, you can grasp the fruit easily, right? That's not the challenge point.
That's right. Yeah. If you give me a lemon or an orange or something or an avocado, it's got a hard skin, easily visible. It's very simple and very easy using our combined information control to be able to harvest the fruit. But when it comes to softer fruit, it's much harder.
So then my question comes like, what is the difficulties and what is the points that like slow down or stop the commercialize of this equipment or robotic technique in a field application?
Yeah, I think when you're dealing when you're dealing with soft fruit like summer fruit, the value to the farmer for a high class crop is much higher than a second grade crop. And the difference between the two is whether or not there are any scratches or any blemishes on the crop. So when you're harvesting as a human, you can actually harvest summer fruit, so like a nectarine or a peach, for example, or a plum. You can harvest it very delicately and you don't damage the fruit. But with the soft robotics, even the slightest squeeze or slightest bump against the twig is enough to damage the fruit, and that's enough to drop the value of the crop to the farmer. So it's not so much the cost of the technology, but being able to ensure the risk associated with being able to ensure that you don't damage the fruit at all. And I think that's at the moment now, that's why we can't use things like, for example, like the apple harvesting that we saw before, or orange harvesting. We can't use that on the soft fruit.
So you mean that to make the robot more delicate, to make sure that the robot will not scratch the fruits or the plants. But how is the like efficiency, like speed of the harvesting? Is that okay, or is that also?
It's a good question, because I think there's a few things that come together. So we've been speaking purely on robotics now, but I think when you talk to farmers and you start to think about what the orchard should look like, there's lots of discussion about how you would train the tree so that the fruit sits nicely for harvesting, even if it's less yield. If you have an autonomous harvester, you still may be able to make some more money, and even if you can't effectively pick as fast as a human because you're working over longer duration cycles, then you're still able to harvest as much fruit as you would with the human. So there's a balance. So when it comes to the efficiency and the economics, there's a balance there. It doesn't necessarily mean that we have to harvest as quickly as humans, but we need to meet the same grade quality as what humans can do.
Okay, thank you.
Thank you. We have the last question. We have more questions, but we will answer them later in the chat. But we will take the last question from the Slido. And Nicolaus asks, did you use the full 6D pose or only 3D position for path planning gripping?
From the robotic arm perspective, it was 6D, but we never looked at the orientation in the field trial. We never looked at the orientation of the fruit.
Thank you. For the additional questions, we will take them in the chat or on Slido later on. And now I will lend the floor to Tommaso for continuing sharing session 2 on multimodal perception.
Okay, thanks, Arya. Hello again, everybody. Welcome back to session 2, which is titled Multimodal Perception for Dexters and Effector. And we have 3 talks now, because one has been already done this morning. So the next up would be Dr. Fei Chen. If it's here, I would ask him for start presenting.
Yeah, I'm here. Can you hear me?
Perfect. Yes, I can hear you. So I will give a brief presentation. Dr. Fei Chen is an assistant professor with Eastern Robotic Institute, the Chinese University of Hong Kong, as well as the Hong Kong Center for Logistic Robotics. His research interests lie in robotic perception, learning, planning, and control for mobile manipulation for a variety of applications, such as manufacturing, healthcare, and agri-food. He's the co-chair of IEEE Robotics and Automation Society Technical Committee for Narrow Robotic System. And this talk today will discuss the challenging problem of grapevine winter pruning, and he will present a novel multidisciplinary approach that tackles this complex task. The title would be Towards Vineyard Automation, Robot Pruning and Harvesting. So thank you very much.
Thank you. Is my slide correctly displayed?
I think we are seeing the presenter.
Okay. What about this? No?
For a second, it was okay, but now we are back to the presenter. That's a little bit better. Yes, here is in the presenter mode.
I need to check it. Strange.
In the meantime, Tommaso, we may encourage audiences and people to suggest some questions for panel discussion. You can put
definitely.
it on the slide or in the chat. We will take it.
Yeah, definitely. As we said before, we have the Slido website. You can pose your questions there. And we have already published it on our website and also on the chat. We will copy paste it again so that everyone else maybe came in later can find it.
Better?
Yes, much better. Perfect.
Okay. So thank you for having me here to introduce our work. My title is Towards Vineyard Automation, Row Pruning and Harvesting. My name is Fei Chen. This is a work that I did before at Italian Institute of Technology. Currently, I'm at the Chinese University of Hong Kong. So basically, what I'm going to introduce is a project. The name is called VNAM. It was a 5-year project until 2022. Basically, it's an effort of 3 groups. My group was basically working on the manipulation, and then there are another group led by Dr. Claudio Samini, work on the legged robots. And then we have a viticulture expert group from the University of Catholic. They provide expertise on the knowledges about everything about the vineyard. Okay, so the idea, first I want to talk about the pruning. The winter pruning, there are 2 types of pruning. There are summer pruning, or streaming, or winter pruning. So basically we're talking about winter pruning. The winter pruning of the grapevines is a labor-intensive operation that is currently done manually. So even if pre-pruned by the machine, so you can see from the picture on the bottom left that usually now in the vineyard there the machine, the vehicle will do a pre-pruning, the cut of the long canes on top, and then there still be required the human to go in the field to do the precise the pruning, from one by one. So on the table in the left, you can see that this is a summary of the cost of the entire life cycle of the vineyard, of the grapevine, how the cost distributed. You can see the major cost is is for the harvesting. Later, the cost is about pruning. In particular, we talk about winter pruning here. The shoot thinning is in summertime, and also chemical spraying. Those are also costly, but not as much as harvesting and pruning. So basically, our goal is try to use robotic technologies to tackle these challenging issues. When we talk about the shortage of the skilled labor, you may know that in the vineyard, basically in the farm, the young people, they went to the big city. So there are also a shortage of a skilled pruner. And also, we hope that by using modern technology that we can build even more sustainable the vineyard. Okay, so this is motivations behind our work. So the pruning, there are two types of winter pruning. One is called guide or the can pruning, which is another one that we didn't tackle. So in our work, we better tackle another one. It's called spur or cordon pruning. So basically, I give you a quick introduction. So you see, basically, you see the grape. Maybe you already see it in the vineyard. It's growing like this style. It's called a cordon style. So the idea is that in the winter time we need to prune the rest cans. Suppose we already have a machine to pruned, then we have only this short part left. Then we need to have the human worker go in there and to prune each of the spur. We call this a spur, and to leave only one shoot. You see the shoot left on it. If we can take a close look and we see, so the idea is that we need to on each spur to keep only one very good one, the bigger one, and then there is also even critical requirement is that to make sure that there are only two buds left on the left the can, and then in winter time, in the summertime, there will be two nice shoots growing up. Okay, and then the grapes will go from there. So the idea, so by doing so that we can maintain the vigor and the nutrition of the two shoots coming from each spur in the summertime. So this is a basic requirement. But you can imagine that the spur, this spur is quite clean and clear. And then when the vineyard, this is only a 3-year or 2-year vineyard, the grapevine. When we talk about 20 years or 30 years grapevine vineyard, then this part is becoming very, very complex. Nevertheless, we still need to find out how to prune it. So before going to the perception part, I talk about the robot. My team was working on basically on the mobile manipulation. Before we were working on the using this technology for the manufacturing cases. So we found this interesting part with a partner on the viniculture. So this is our robot, and we have the mobile platform, and we have arm sitting on top of it, and then we have a tool with a camera in hand. Okay, this is basically the concept of the robot that we do. So the important part you must is no difference with other people's work. The perception part is very important. So basically, we come out the entire not a complete one, as complete as possible that we can come out. So the idea is that first we use some perception algorithm, the detection algorithm, that we can find out the regions that contains the spur, okay, distributed along the cordon. So we call the PPR the potential pruning region. And then we have the robot going approach that particular region one by one and do some precise the perception on it. Basically on this, inside of this pruning the PPR region, we applied the segmentation algorithms. Okay, yeah. So then then we use a segmentation, and then we apply some post-processing algorithms, and then we use the topology ideas that we based on the segment different parts, that we create a topology of different parts to find out the spur, the cordon, the arm, and the shoots and the knots on it. Then we have the post-processing to find out which can is the best one and that we want to keep. And then we just need to find to keep only 2 knots, butts on it. This is how the close look at our perception algorithm. You can see it can somehow give a very the good results of the segmentation of different parts of the grapevine here. So this is cordon, this arm, this is spur, and these 2 cans, and this is the knots. Okay, so we create the topology graph on it. So also you can see when the situation becomes more complex and we need to deal with some other the possibilities, and our topology construction could be adaptive to different configuration of the spurs and the shoots. Okay. Then in 2018 we had an experiment which is on top of the table, we have the arm that we test the first few pipeline blocks in the pipeline, the detection of the potential pruning region. And then 2019, we bring this technology to our mobile manipulator, and then perform some simulate some pruning on it. At that time, we still didn't bring into the calculation of these 2 knots. Okay, and then this year, 2021 March, that we did a further step. We have our new clipper, and then on the right you can see our whole pipeline somehow can lead the robot to prune the can, and then keep 2 knots on it. So that's something we want to achieve. Okay. And also later, the idea is to not just to put this arm on our wheeled platform. We are considering the challenges introduced by the terrain in Italy, and we are considering using the legged robot with the arm to do the experiment. And we cooperate with the lab, DLS lab, led by Dr. Claudia Osemini. So they basically they make very nice quadruped robots with this Haiku Real one had 130 kilogram and 130 centimeters long. It's very strong, can pull a small air jet. Okay. And then it is able to adapt to move on very challenging terrains. So we are considering testing it in the challenging terrain introduced by the vineyard. Okay, so so this is still the current work. We are now we got a new arm. We put it on this robot, and hopefully soon we will have some nice video coming out. So while we were during the pandemic last year, where with my team was working on the pruning, we also applied a similar pipeline to the harvesting to test if it's okay for harvesting. So basically, we developed the deep neural network to detect the deep peduncle of the stem of the grape cluster, and then this is our experiment that the robot can somehow harvest this kind of table grape by using our pipeline. And also here is this is a clipper that we designed for this harvesting, the simple and the cheap one. Okay, so yeah, this is the end of my presentation. Thank you very much. I'm open for questions.
Thank you very much for your talk. And if there are questions, please raise your hand, and because yeah, we have time for questions. I think, okay, Amir, please.
Thanks, Tommaso. Thanks, Faye. Very interesting talk. In your view, what is the main challenge to make kind of robotic system that can do selective harvesting of grapes? So what is the key, let's say, bottleneck? Is it the hardware development? Is it the, let's say, the intelligent components that needs further development? So where we are lacking that kind of development?
So you mean the challenges introduced by the table grape harvesting? So basically, if we talk about it, okay, if we talk about the grapes for wine, we don't need to harvest, right? We directly use the machine. They can just take them out. Doesn't care about the damage. For the table grape harvesting, so we need to we need to take care to select the best one, you know, that contain the very the nice content of the sugar in the grape. So basically, the skilled worker can go in there and select the best one to cut, not just one at the one day. Maybe they come at different days to find the best one to cut. For the robot to do so is very challenging. So there is right now we need to, first of all, about sensing, we need to find the right sensor, try to get this the content of the sugar, and then we also need to consider the occlusion that introduced by the overlap of the clusters to make sure that all the stem can be always correctly detected. So currently our algorithm is somehow working, but so this is just a test that we did last year. So our perception algorithm is still not so perfect for the stem detection. Hopefully, we should improve it, considering more different scenarios. But regarding putting aside the harvesting, I would say the winter pruning is a very challenging task. So this is basically the main purpose of the object, not the table grape harvesting, but the winter pruning is the goal. Yeah.
And how long you think we are far from technology deployed in the field for pruning, winter pruning?
Well, depends on how far that I think there is no limit here to push, because this is we still have a long way to go. For example, now currently we output the pruning detect points, right, in the 2D image. We still not yet consider it's currently one of the PhD work. Student work is try to find out the pose to prune the can, because because we are collaborating with the professors, they are studying viniculture, so they give us a very critical requirements, like they hope that the cutting section should not be flat, should be with an angle to avoid the liquid or chemical rest on top of it, and then generate some bacteria, you know. So they hope that always cut with the angle that to avoid anything accumulate on top of it. But when talk about the workers in the vineyard, they don't care. They just probably just simply prune it. Maybe they didn't think too much about what is the best pose to prune. So depends on, yeah, the answer is depend on the requirements. If from the experts, they wish that we can do as further as possible. So we hopefully in a couple of years we can do some field testing. Yes.
Cheers.
Okay, thank you. We have time for a very quick question. We have a question from Qingyu Wang. So, please.
Hello, Qingyu.
Hello. We cannot hear you. Okay. Do you want to
I can tap him. Yeah. I can send him a message in case he has questions to me. Yeah.
Okay. Yeah. Okay. Perfect. Okay. If we don't have any more questions and we take this one offline, thank you again to Dr. Chen. And we can get to the next speaker, which is Massimo Roa. Is Dr. Massimo Roa here?
Yes, I'm here.
Perfect. Okay, so I would ask you to start presenting, and I will give you a little bit of introduction. Dr. Massimo Roa is a senior scientific researcher at the Institute of Robotics and Mechatronics in the German Aerospace Center, DLR. He is a group leader for robotic planning and manipulation, focused on development and implementation of locomotion and manipulation skills at different levels of industrial service and humanoid robotics. Today, the Dr. Roa talk presents the main feature for the Clash Hand, a compliant and effective developed specifically for food handling. And the title would be Compliant and Effectors for Food Handling, the Clash Hand. So very glad to hand over to you.
Thanks. Should I let me try. Please confirm if you're looking at my screen or at my slides.
Yes.
Okay, cool.
I'm looking at your screen, I guess. Yes, you have the presentation on.
Yes, perfect. Thank you very much. Thanks a lot for the introduction and for the nice invitation. It's a pleasure to be here. So I want to present you the Clash Hand. This is a development that we did in a European project that finished a couple of years ago, and we've continued developing at DLR. So some of you might have already heard the first part of the talk, where I will present some quick snippets of the development of the hand, and then I will move to the second part of the talk, which is how we are doing the benchmarking, how we are testing this hand, which is actually the novel part for this talk. So indeed, the Clash Hand was developed specifically for handling fruits and vegetables. So let me tell you a little bit about the development process and the main features of the hand before telling you how we use it. We started this project SOMA with multiple partners, among them TU Berlin and IIT and University of Siena. And the idea was that we could exploit the way that we use as humans to grasp objects, but with robots. So basically, if we compare, most of the robotic applications have this way of grasping objects where the fingertips go to grasp the object without any contact with any other object in the environment. But humans skillfully use the contact with the environment to cage the objects and to secure a very robust grasp. And this was one of the driving ideas behind this project SOMAS, which stands for soft manipulation. The second idea was the use case brought by Ocado technology. You had a different use case, but this one is the one that is related to fruits and vegetables. So Ocado is the largest online-only grocery store in the UK, and they have multiple stations where they have to basically pack fruits and vegetables and meat into individual totes for fulfilling a customer's order. The thing is that most of these products have to be kept at a temperature which is, of course, in a cold chamber. We're talking about 5 degrees or so. And workers at these areas can only work in shifts of 20 minutes and then 40 minutes rest. And even on the cold chambers is much lower times. So this represents a huge problem in terms of health for the workers, of course, and productivity in terms of the company. So the idea was, okay, can we develop a hand that can handle fruits and vegetables in such a way that they, of course, fulfill the purpose of grasping them and manipulating them, but also reduce as much as possible the damage to the fruit, because a damaged fruit will be returned by the customer, which is, of course, not desirable in the logistics domain. So this was the use case. And we started with this robot. You might have seen it, is the hand arm system from DLR, developed some years ago. It's one of the most advanced humanoid systems in terms of functionality in the world. So it has variable stiffness actuation, meaning for all the joints we can rigidize or make them soft to perform different actions. So this is a really nice system. However, it's very complex. To bring you the example of the hand, here you have it. The hand has 20 degrees of freedom, but because of the variable stiffness, we have 40 motors to drive the hand. So 40 motors, of course, they don't fit into the hand itself, so they have to be allocated on the forearm. This creates a huge weight. It's not a hand that you can place on top of any robot, typical robot. It's very expensive and has some additional challenges, like for instance, how to distribute the power created by the electronics of all of these motors. So the idea in SOMA was, how could we simplify this development to get hands that can keep as much of the functionality, but with a much simpler and a much cheaper design? So we tried this in the project. We moved, for instance, for a 2N actuation, agonistic antagonistic, to an N+1 actuation. We kept under-actuated systems, and we kept the variable stiffness actuation. We came up with 2 prototypes. The first one was the whisk hand. This was just a proof of concept. We actually used it only for a couple of experiments and 1 master thesis. And we developed the clash hand, which we are continuing developing right now. So this hand was intended for this use case of fruits and vegetables in the logistics domain. What we did was, on the design rationale, just simplifying the most common SKUs that they had at the factory, at the warehouse, into simple geometric shapes. Here, spheres, capsules, and cuboids. Of course, you can imagine that these not only represent a lot of fruits and vegetables, but also a large portion of everyday objects. With this, we perform the kinematic and dynamic design of the hand. And to give you a quick overview, this is how it works. So we have 2 main modules. One module which we call parallel or differential fingers on the left, and one module for the thumb on the right. Each one of the modules has 4 servo motors driving the fingers, 3 for the DOFs of the fingers, and 1 for the variable stiffness mechanism. That means we have only one that can rigidize or make soft the full finger. You can see at the bottom the matrices for the coupling. So basically this indicates the individual rows or the individual DOFs, and the tendons are in the vertical direction. So this tells you basically how each tendon affects the DOFs that are included on the hand. Good. The variable stiffness actuation was achieved through what we call the flexible antagonistic spring that you see on the figure on the left. So this is basically one tendon and pulley system, spring system, and it basically rotates and then increases the tension on this tendon, therefore increasing the stiffness. This gives several advantages. One that you see on the video that is playing right now, the robustness. So we use our standard DLR hammer test. We just hammer the fingers and see if it resists or not. But we also achieve a very sensitive manipulation. So you see here the finger, for instance, being touched by one standard business card, and you see how the finger has this nice mechanism that couples around, tries to wrap around the object as soon as there is one contact in any of the links. So it's both very robust and very sensible. This is a table of comparison of the performance with different factors for different DLR hands in terms of fingertip force, the weight, and the cost. And basically what you can take away from this hand is that we achieved a very high fingertip force with a very low module weight and a very low cost. Good. We achieved, of course, successful grasps on different scenarios, both for standard objects, the YCP database, for instance, the intended objects, the fruits and vegetables, and also very delicate objects. You see here strawberries or these small biscuits. So we can tune the stiffness and the force threshold such that we can apply just enough force to grasp the object. With this, we also also managed to do what we called exploitation of the environmental constraints, meaning we don't not only grasp the objects by the traditional going to the object and putting the fingers around and grasping them, but also using the fingers or the contacts with the environment in a productive way to gauge and to retrieve objects that are hard to grasp in a different way. For instance, you saw on the left grasping a ticket, and on the right what we call a wall grasp, where we just cage the object against one of the walls and then we grasp it. Good. So this was the development of the clutch hand. And what is interesting about this development, and the point that I wanted to bring here, is how to benchmark these developments. We see multitude of robotic hands, multitude of robotic grippers. How can we actually make sure that the one that we are using is good for the application that we have? We have worked on this topic on the last 3 or 4 years with different people and trying to come up with different tests to verify the performance of the hands. You see here on the left side, the rational evaluation. We don't use the hammer anymore. We just use now this impact pendulum to test the robustness of the hand. In this case, we try and see how much energy can the hand resist before it is broken. And on the right, you see what we called the resilience, the hand and grasp resilience. So basically understanding by resilience how the hand behaves under the dynamic loads, and by grasp resilience, if the grasp is capable also of resisting dynamic loads. Okay, I have some problem with the video, but basically this is again an impactor hitting the object that is being grasped, and we measure the energy that we can resist while still keeping the grasp in the hand, keeping the object in the hand. Good. Other type of benchmarks that we use were grasp performance. So we use, for instance, this setup on the left that you see. We just place the object on a predefined pose with respect to the robot coordinate frame, and we approach the object with different orientations and different elevation angles for the hand, and we try to grasp it. So basically, this indicates how the grasping ability of the hand changes with these two variables, the approach and the approach to elevation and the hand orientation. And we generate these heat maps. White is better, so the whiter the map is, the more successful the hand is for grasping the object. In this case, we were testing different failures. This is what is interesting for these benchmarks. We basically introduced different verifications to try to recover from errors that might arise during executions. We have verifications at the beginning of the performance of the execution. We have verifications during the working conditions, or grasp verifications during the grasp action itself. Some of these tests can be executed only at the beginning because afterwards they distort the position or the force control, but some of them are also needed to verify if the grasp is successful, and if not, trigger recovery action. And this is what we did on this paper. So we compared the baseline performance on the blue bars with artificially introduced errors on the hand. We basically created different errors like disconnecting one tendon or disconnecting one motor or one sensor, and try to come up with different strategies to cope with these possible failures and guarantee still a successful grasp. We were actually quite happy with the results. However, all of these, I must say, are hand-coded strategies. And one of the things that we are really looking forward to work on is how to learn these strategies on the fly, such that the programmer doesn't have the task to come up with all these different strategies. The other thing that we've been doing is working on the planning of the full pipeline. So we use here, for this scenario that you saw at the beginning, which is also typical in logistics, also in filling scenarios in supermarkets, we have these bins which are very crowded with objects, and we need to empty the bin. So how to do it in a rational way? The trick is always how to successfully grasp the first couple of objects. Once you have enough room in the bin, you can easily grasp the other objects. So for this, we combined the visual detection algorithms one algorithm for finger placement, such that we look for the small free spaces around the objects, and one stiffness selection tree, where we basically exploit these capabilities of variable stiffness to tune the stiffness that we need depending on how fragile the object is, how much uncertainty we have on the position of the object, and how cluttered the scenario is. We actually managed to implement this for this scenario that you saw a moment ago, the mangoes, based also on a global score that we explained on this paper that includes, for instance, the reachability of the arm. We trigger the grasps and we try to grasp the most accessible object. Once we have that object and we put it on the bin, then proceeding with the other objects is much easier. We tried this scenario also on different levels of clutter, and we were actually quite successful on these scenarios. Good. There are, however, challenges that are still left out there. This is one of them. So imagine now that we have not mangoes, but punnets. The space which is free for grasping them is much smaller. And you saw here one of the strategies that we implemented, which is poking the finger, moving it to the side of the punnet, and then lifting it to be able to successfully grasp it. How can we systematically test this? So we came up also with a bin picking benchmark with the other people, where we created these different scenarios that you see on the slide. Those scenarios, of course, change in complexity, and basically the high clutter scenarios were very hard to reproduce, to solve with the grippers and with the strategies that we had at that moment. These are the grippers that we tested. We tested the IIT hand and gripper, the RBO hand and the Clash hand. And you see on the right, the success rate on the top and the types of failures that we got. So benchmark, on one hand, gives you one systematic way to test your development, but on the other hand, of course, compares your development with what other people is doing. And this is actually, of course, challenging for the development team, because then you realize, we are the yellow line, and we are having a lot of grasp fails, if you see on the bottom right figure. So how can we improve that? And this triggers the development and the iterations. We are actually right now on the second mechatronic iteration of the hand, where we are trying precisely to solve these use cases. So in particular, we focused on these two scenarios called C3 and P3 on the original paper. And we try to solve them with the combination of suitable fingertip sensing modalities that are accommodated on the tips of the Clash hand. So you see here an overview of the sensors that we are testing to provide information on different modalities. So pressure, acceleration, closeness, time of flight sensors, and also the typical tactile matrices. So exploiting this information, actually, I can say that successfully managed to solve these two scenarios. The video and the paper is submitted, is under evaluation right now. So I hope that once it is published, you can see the way that we used to solve this challenge. Good. So this is all I wanted to bring you today as a contribution to this talk. Some final thoughts. First, we showed how the variable compliance allows you to adapt to different objects. And also important for us, we can independently tune forces and stiffnesses. That means when we change the stiffness, the fingertip can be independently controlled for the force, and also can keep the position that it has while grasping. We use extensively these benchmarking protocols, which allow to have these straightforward comparisons in performance between different grippers and guide also your developments. And also a suitable combination of sensing and manipulation planning, which we use to solve difficult scenarios. Just as a closing video, this is one of the things that we are actually very actively working on, error recovery. We recognize that you can fail the first time, but you should not fail the second time on the same challenge. So what we do is exploiting this information that we have on the hand and the fingertips to be able to trigger recovery actions in an automatic way, such that you can actually solve successfully the scenarios that you have, in this case, in the logistics domain. So that's all I wanted to bring you today from my side. Just a final acknowledgement to the people that is part of the team, and the webpage of the SOMA project, where you can find additional information on these developments. So thank you very much, and I hope we can have some couple of questions for me. Thanks a lot.
Thank you very much. It was a very interesting talk, so thank you. We have a couple of questions. Let's go first with Lorenzo Iamone. So please.
Yeah, thank you. Hi, Maximo. Thanks for the talk. Very interesting. I'm curious about. So you mentioned these different strategies that you may have to use with the hand in order to grasp object in, let's say, very difficult clutters. Do you have like a list, let's say, tentative idea of how many of these strategies are there to be implemented, and if in your case, like you're trying to implement them, let's say you hard code those strategies, and yeah.
Okay, yeah. So the efforts that we have are more directed towards creating automatically these strategies. So with this combination of tools that I showed on the video, for instance, combining visual perception, the grasp planning, the fingertip planning, and the dexterity of the arm, we try to let the system automatically decide what are the best strategies. Of course, in some cases, you can hard code strategies. In the one that I showed with the punnets that are filling completely the bin, this was hard coded. We just poke the finger, move it around, and then lift the punnet and try to grasp it. This is, of course, possible, and this shows that the technology that we have and the hardware is capable of solving these tasks. The challenge that we have right now, and what I welcome, if any of you have a good idea for collaboration, it will be my pleasure. If we can come up with some system that can be learning-based, can be model-based, but that can automatically come with these strategies of how to effectively use the capabilities that we have on the hardware to basically try to solve these challenging scenarios.
Thank you.
Okay, thank you. Thank you for the question. And we have another question from Mahmed Dogar. So please.
Yes.
Hi, Massimo. Thank you for the talk. I wanted to ask, with the clutch hand, we have variable stiffness and force, but that doesn't mean, probably, if it does, that doesn't mean that we can control the amount of force we can apply, does it?
We can, yes.
So, okay. So, and does that mean, is that through calibration? Because given a certain stiffness setting with a certain displacement, you have an idea about what the force is, or do you have, can you do closed loop control on the force that you're applying?
Okay, good point. Yes. So actually, this raises a very interesting scientific question that we are dealing with right now. So we can tune the passive stiffness of the system, so the mechanical stiffness, right? We have this flexible antagonistic spring that we can tune, and we can change the range of stiffness for each of the fingers. And then we can also control the force. So there is one servo that controls the stiffness, and there is a different one that controls the opening and closing of the hand, and we can use that one to implement a standard torque force-based control. So we can do that independently, and this is one of the nice advantages. However, we are not exploiting that to the full level right now. And this is, this is just a challenging question for us, and this is under development. We are tuning stiffnesses with this stiffness decision tree that I showed, for instance, at some point. We are setting the stiffness to low, medium, or high, but we don't have discrete levels. We have a continuous range of variation that we could exploit. But right now, I must say, we don't have the tools to exploit effectively this range of variation. And this is one thing that we can exploit right now. And then the second one is we can also use them not in a one-time setting, but in a continuous setting, like we humans do. We not only set our hands to be very rigid and grasp the object, but we are continuously adapting the stiffness and changing it as the manipulation action progresses. And this is something that is also extremely interesting for us, where we are trying to take the first steps in this direction. So yeah, really, really interesting topic.
Thank you.
Okay, we have another question from Saria. So please, Saria, go ahead.
Hi, Dr. Maximo. So thanks for your talk. My question is also related about variable stiffness actuation and the integration and the ND factor for grasping different objects that you mentioned on. I have a work here that investigates into learning a policy that from a human being in order to learn when picking an object in a cluster, not on from a bunch in a box like you showed. Like learning when the hand approaches the cluster and enters into that cluster, we want to see if the stiffness in pickers in human hand changes before entering the cluster and after entering the cluster. My question to you, from your experience in variable stiffness actuation, do you think that this can help picking more accurately or picking more efficiently from cluster if we embed variable stiffness actuation in the manipulator in the field?
Yeah, definitely. This is also an interesting scientific question. I know that at the end of the SOMA project, the people at Ocado tried to do some studies in this direction, like having sensorized gloves and trying to see how human pickers actually change the properties of the hand of the end effector to be able to grasp different objects. And especially for them, it was interesting how this has an influence on the speed of picking, which is at the end the metric that they have, right? So if they were putting more pressure on the picker to be faster, how this stiffness was changing while they were doing the picking action. So this is interesting, and I think definitely the variable stiffness actuation offers you a lot of advantages in terms of manipulating both rigid and fragile objects. We can manipulate objects, for instance, with 0.1 newtons of force threshold for application of the forces, but we can also grasp lettuces or coconuts, which are 2 kilos, 2.5 kilos, and relatively large objects. So this property, in principle, for sure enables you to exploit different environments in a nice way. Also, in some of the examples that I showed, for instance, we change if we poke with the fingers on the physical space between the objects. We usually try to use high stiffness because we don't want the finger just to deflect as soon as it touches the object. We want it to go into one specific place. But afterwards, we might be able to change the stiffness back and make the finger compliant such that it can adapt to the environment. So there are different applications that we have on this. On this IROS paper, we have some of them, and we are working on some other applications. But yeah, this is definitely one topic that I think is a nice research topic and is not fully exploited still.
Thank you very much. Thank you.
Yep.
Okay, I think we are there with the time. Thank you again to Massimo. It was a very, very interesting.
Thank you very much.
Okay, so the next speaker is Lorenzo Iamone, which should be here. Cool.
Hi, everyone.
And okay, so if you can start presenting. In the meantime, I will give a brief introduction. Dr. Lorenzo Iamone is a senior lecturer in robotics at the Queen Mary University of London, where he is leading the CRISP team. He received a bachelor and master degrees in Genoa, University of Genoa, and also his PhD at the University of Genoa and the Italian Institute of Technology. And his research interests include sensory motor learning and controlling human robots, robotic reaching, grasping and manipulation, and intelligent system and cognitive development robotics. Today, his talk will do about robotic dexterity and how we can work with soft tactile sensor for increasing and enhancing the robotic manipulation for quality control. The title is Tactile Sensing for Robotic Manipulation and Fruit Quality Control. Thank you.
Yeah, thanks for the introduction. Just let me know if you can see my screen and you can hear me well. If anything goes wrong, just please shout and let me know.
Perfect.
All right, so yeah, hello everyone. My name is Lorenzo Iamone. I'm senior lecturer in robotics at Queen Mary. Thanks for organizing this workshop, by the way, very interesting so far. So I'm, for those of you who do not know Queen Mary, we are one of the universities in London. We are a Russell Group university, among the best universities in the UK. And we are very proud also to be a very diverse and inclusive university. And I am part of ARC, the Robotics Center at Queen Mary, that was established about 4 years ago and is led by Professor Kaspar Althofer. And we do a number of things in robotics. We focus on both hardware and software, including soft robotics. For example, Ketao Zhang is also doing soft grippers. That is related to some of the talks we saw before. Myself, I mainly work in manipulation and tactile sensing. And I lead a team that is called CRISP. It's Cognitive Robotics and Intelligent Systems for the People. And in fact, our objective is both to create intelligent robots, taking some sort of inspiration from biology and human behavior, but also to try to understand something more about human intelligence by doing this. And this aspect I will not focus on during this talk, but this is something that I care about in my research, in our research. And this is a picture of the team. Specifically, we focus on the intelligence of our hands. So how can we use the hands to grasp and manipulate objects, and also to explore objects and gather information about them, but also to use the hands to improve our perception and to communicate with each other. And we have a number of projects funded by several funding bodies in the UK and also in collaboration with some companies. And I would like to quickly mention two of our projects, the MAN3 project and the NCNR. So the MAN3 project is a human-inspired robotic manipulation for advanced manufacturing. And this is also connected to some of the previous talks. We saw in one of the first talk the importance of learning from human demonstration. And here we want to do that, but using teleoperation as a way to provide the demonstrations to a robot. And in this project, we collaborate with Ocado, the online supermarket that was mentioned in the previous talk, and also with the Shadow robot company and the Google DeepMind. And the idea is that we developed a teleoperation system that is very cost-effective, it's very cheap. It's based on lip motion to track the finger and then some vibrotactile feedback on the user so that the user can feel what the robot is touching. And in fact, we are looking at specific problems in picking objects within boxes, taking the use case from Ocado. And here, in fact, we think that by using a multi-fingered hand, we can probably discover interesting strategies that the user that is demonstrating to the robot will use in order to pick the object. For example, and I will show maybe this again. So for example, if you have a clutter of objects, for example, several lemons there, and you cannot pick them fully with all the fingers, maybe you can pick them first with 2 fingers, and then only during the transport phase, you will grab the object with the rest of the finger. That's just one of the strategy. And we are looking here at discovering this strategy automatically from demonstration provided by users. And another large project we are involved in is robotics for nuclear decommissioning. This is the NCNR project, National Center for Nuclear Robotics. And within this project, we have a number of activities. Myself, I mainly do the tactile sensing and grasping and manipulation. And so how does this fit with this workshop? Well, in general, is about using tactile sensing for robotic manipulation with two main objectives. One is to being able to handle challenging objects, for example, objects that are very delicate, by applying just the right amount of force. But the other aspect is to obtain additional information about those objects while they are being manipulated through tactile sensing. And in this direction, I've been working since several years on tactile sensors based on magnetism and soft materials. And here are two examples of two families of sensors that I've been working on. One that is roughly inspired to the Merkel disc in the skin, and the other one that is inspired to the hair receptors that we have on our skin. And I will tell you briefly how do they work. And of course, there is a longer presentation on YouTube in which I provide a lot of details on their functioning. But the main idea is relatively simple. So you have a magnet that is immersed within a soft material. And then you have a magnetic sensor that will measure the magnetic field generated by the magnet. Now, when the soft body is deformed due to a contact, for example, a force applied, then the magnet will be displaced, and therefore the magnetic field measured by the sensor will change, and this will give an indirect measure of the applied force. And as you know, there are several technologies that you can use to do tactile sensing and force sensing. We believe this technology, magnetic, is particularly interesting because it provides very high sensitivity to the measurement and very high signal-to-noise ratio. So we can have a robust measurement of very low forces. And this, for example, allows the manipulation of delicate objects, as you see here in the video. And this work has been done in collaboration with several people, including people in Waseda University in Tokyo. And you see here how the object can be gently manipulated, and also we can detect slip and get information about, for example, the change in weight of the object. And with a different version of the same sensor, which is not conformed on a fingertip, but is flat, and so better shaped for parallel grippers, we are now doing some work on detecting slips. And here you can see some of the readings from the sensor. In this case, is a matrix, is a 3x6 matrix. Each of the elements measures the 3D force, so it's a lot of information that we can gather. And in fact, what we saw from these initial studies is that even if we do data collection, let's say in the wild, so while the robot is doing normal grasping operation, we can then use the data to build classifiers that are quite good at detecting slips and non-slips of the objects. And by the way, this sensor here is also commercialized by ICRA Robotics. You see the logo of the company in the bottom left. And in addition, we can, of course, do something like object recognition. And if you see some examples of the tactile signatures that we obtain of those objects, you can see that even considering different grasps of the same object, we can see some similarities in the tactile signal related to a specific object. So clearly, this data can be used also for object recognition. And the other family of sensors is inspired to this cilia concept. And in this case, it's a tiny soft pillar in which we embed ferromagnetic particles. And then we magnetize all these particles along the same direction so that the cilia becomes actually magnetic. And then it's the same concept. The deformation of the cilia is measured by the magnetic sensor below. And this is even more sensitive because of the magnetic approach, but also because of the physical structure of the sensor. And we applied this to fruit quality control, and we tested with different fruits. So we collected some data swiping these cilia over the surface of the object and collecting some data. And then we extract specific features from this tactile signal, and we use that for classification, and we could classify the different fruits, apples and strawberries into ripe or senescent. And this is a paper at IROS last year that was awarded, was the best paper finalist in the Agri-Food category. And next step will be then to combine these two things and have sensors and say grasping strategies that could allow to both handle delicate objects, but also understand something about their quality or, for example, the ripeness during the picking. And the image here is just illustrative, is not a system that we own or that we are deploying. But something just to conclude additional that I'd like to mention, in order to deploy this system in which we have different robotic components integrated together and different software components that have to be integrated in order to control tasks, we developed a software framework that is called GRIP. This has been recently published in the Robotics and Automation magazine, and there is a link down if you want to check more details about this. But this is basically a software framework that will allow naive programmers to easily design and deploy robotic tasks. And it is built upon ROS, but it has a friendly user interface that does not require the programmer to understand to understand ROS in details. It's just based on configuration files that can be updated, and then a task editor, a visual task editor that can be used to program different robotic tasks and to monitor them during execution. And we applied this to a number of tasks. Here you see one in which we are using the dexterous hand from Shadow Robot to perform this relatively complex task. It's not very complex from the motion planning point of view, but still, because we have two different robots that they have to be integrated, this will not be trivial to be executed, to be programmed. And in fact, we did a user study, and we asked naive programmers to use this system to program robotic tasks. And we saw that even people who didn't have experience in robotics, they could easily program tasks in 1 or 2 hours, which is a very quick time, even for more experienced robotic user. And of course, we can also design tasks that are much more complex, like this one you see here, in which we integrate vision and movements and different decision trees that will allow the robot to decide to monitor whether the object has been picked, and if not, to do the action again, so on and so forth. And with this, I conclude a quick summary. I have introduced some tactile sensors that are based on soft material and magnetism, and discussed how they could be used for, well, in general, to handle delicate objects and also to obtain additional information about those objects, and a software framework to deploy robotic solutions. And that's me. Thank you very much for the attention.
Thank you very much for the presentation, which was interesting. Do we have any questions? Okay, it seems not. Okay, we have one from Amir, please.
Thanks, Lorenzo. Very interesting talk. So we know that just working with the tactile sensor, magnetic-based tactile sensor has some limitations. So if you are close to some magnetic field, then you're getting some noises. Is there any kind of workaround to this problem in your view?
Yeah, that's a good question. So the main, in fact, that's the main limitation of the magnetic sensing. The main way to alleviate the problem is that you can have an external magnetic sensor that would also detect a possible external magnetic field, and so then you can compensate for the external magnetic field. Unfortunately, let's say the bad news with respect to magnetics is that you cannot really shield magnetic fields. So there is really no way around that. But the good news is that the influence of a magnetic fields decrease quite rapidly with distance. So unless you're really very, very close to a magnetic source, or the magnetic source is incredibly strong, then you don't really have interference. So it's I would say it's quite limited set of scenarios in which you will really have those kind of interferences. And if you expect to have them, what you can do, as I said, is to have an external reference sensor and compensate for the external magnetic field.
Thank you. Yes.
Yeah.
We have another question from Alexander Schmitz. So if you want to go back, please.
Hi, Lorenzo. How did you implement the sleep detection? Was it machine learning or was it model based?
Yeah, so for the sleep detection at the moment, we have tried with the relatively simple classification methods. We're using random forest classifiers, and we have tested with a number of different features. So of course, with this sensor, you know very well because you have been working on them. But so with this sensor, you measure on each point both the normal and the shear force is applied. So we have tested a bit different features that we can use using either only the normal force or also the shear forces, etc. And but we have already relatively good result with using relatively simple classification methods. The plan for extensions to this is to use the CNNs so borrowing from vision, to try to better exploit the spatial arrangement and the spatial, let's say, similarities that you get in the different taxels, and also a recurrent version of them to exploit also the temporal features. So, because of course our measurement in this case are distributed both spatially but also temporally, and so we think as an extension, recurrent convolutional neural network could be a way to exploit both aspects, but we haven't tested so far.
Okay, thank you very much.
Yeah.
I have a question about the software, the last software that you presented. Can you tell us a bit more how it works? I mean, it is upon ROS, you said, and you can import everything that is already importable on ROS. Do you have some software, some robots and gripper that works with specifically with that? How does it work?
Yeah, so I think really our target with this was to both facilitate the deployment and integration of different components. So to facilitate for everybody, even people who are experienced with ROS and with programming, and to make it more accessible to people who do not have experience. So in practice, if you have to integrate components that are already ROS friendly, then of course you can do it, and it will make just your job much easier. And because you have also these visual graphical user interfaces. If you have to integrate components that are not ROS friendly, they don't have ROS drivers, then you can also integrate them by using interfaces that we provide as examples to integrate other systems that are not ROS compatible. So it provides also an advantage in this sense, because ideally you can also integrate things that otherwise it will be even more difficult to integrate together.
Okay, thank you.
Yeah.
Okay, if we don't have any more questions, which appeared the case, I think we are finished with this session. Thank you very much for everyone that has participated, and we will move to the next section that will be chaired by Mahmed. So
yes,
I will hand over to you.
Thank you, Tommaso. Thank you. Well, hello everyone. So we are moving into the next session. I realize we didn't put any breaks in this, and maybe we should have. But
do we need a break? If this is the case, probably we can take a 5 minutes break and come back. But otherwise, we can go on. I
mean, I guess people have been taking breaks, right? Since
like
frankly, I did. But if anyone thinks we should definitely take a break, please raise your voice, and then we can, because it seems like we have time. We are since we had some speakers missing, I think we have time. But okay, then let's go to the next speaker. So first of all, in this session, there is a pre-recorded talk by Mark Hanhade on mobile robotics and HRI in the fruit harvesting chain. To listen to that, you can go to the YouTube channel later. Is that right, Saria? Yeah, okay. And therefore, we will then be going to the next speaker, who is Zuoling Han. Zuoling is a PhD student at the Department of Computer Science at King's College London. Her supervisors are Professor Simon Parsons and Professor Elizabeth Sklar. Her research interests are on the design of automated fruit harvesting robots, especially strawberry picking robots that can work in complex environments. Zuoling, hello, nice to meet you.
Hello, nice to meet you.
Can you try sharing your screen and you can make sure?
Yeah, so can you see my screen?
Yes, I think it's all good.
Okay.
Please go ahead, Zuoling. Thank you.
Okay, thank you. Thank you for the introduction and thank you for having me here. So my name is Zuoling. I'm a PhD student at King's College London, supervised by Professor Parsons and Professor Sklar. So today I'm going to introduce a piece of work about planning the harvesting sequence in complex environments for strawberry picking robot. So the basic process of strawberry harvesting could include tasks such as identifying ripe strawberries, controlling the robot arm to approach the target, and removing the fruit from the plant. So below here shows some examples about strawberry targets. From left to right, the complexity is increasing. So when harvesting with a robot in the real farm, the complex cases are very challenging, but usually unavoidable. So far, the main bottlenecks in current strawberry harvesting robots are single image detection rates and harvesting cycle time, according to some research, especially in complex cases when new obstacles and targets might be detected when moving the robot while harvesting. So cycle time can be improved by optimizing the harvesting sequence, and there is still room for improvement in planning the harvesting sequence for strawberry harvesting. As the number of targets and the number of obstacles around the targets increases, using exhaustive search to find an optimal harvesting sequence within reasonable time is not that feasible, and heuristic approaches must be sought. So here we describe steps towards learning from human pattern of harvesting. We used a virtual environment, which is a visible approach to collect data for such research, and a convenient way, especially during restrictions on doing experiment face-to-face on campus due to the lockdown. So the arrangement of fruits in three-dimensional is simulated from the distribution of strawberry in elevation and plant views, respectively. The model is derived from a dataset has images taken in 2019 in polytunnels at Risenham, Lincoln in the UK. So the strawberry plant model used in the video game ignores leaves and only presents the distribution of strawberries. The strawberry models were created using a software called Blender and can be easily distinguished from each other by their colors. So as shown in this slide, the obstacles in the game include green strawberries and also rotten strawberries as shown here. So the video game is a WebGL project created with Unity. The game is uploaded to a web page, so the user can play the game easily with their own device, even during social restrictions. So it provides 3 different modes, the training mode, easy mode, and hard mode. The training mode introduces the game to the user. So before the user officially starting play the easy mode or hard mode, it's better to try the training mode first. Here is an example of the easy mode showing in this video. easy mode simulates human strawberry picking by requiring user to click on the ripe strawberry to harvest them. So when the mouse is on a strawberry, it will glow to help avoiding click on a strawberry unwanted by mistake. So here's an example of the hard mode. Hard mode simulates harvesting by a robot gripper. Thus, the user needs to move the gripper with the keyboard to a suitable area above the target strawberry, and then press a key to harvest it. Like in all modes, the user can shift their viewpoint in the game. The viewpoint is that of a robot. So there are 4 parts of data collected anonymously. So first, the score. Only game records with full score are used in our analysis later. And strawberry map, it is all the strawberry fruits location and their type. Red ones as target and not red ones as obstacles. And strawberry collected order, which is when is each strawberry being collected since the game started. And the movement record, which is how the user moved the gripper or the camera. So the operation data for each player is collected anonymously and sent to a cloud database after each round of the game, and is cleared from the cloud storage and moved to local storage at intervals. So in each game, ripe strawberries are collected in sequence. When a ripe strawberry is selected, it is considered to be a better one than all the others in that situation. We call each situation in which such a choice is made a scene. So to simplify the description of each scene, the selected strawberry in a certain scene is then paired with all the other ripe strawberries in the same scene. The choice made by the user means there's always a preference between each pair of strawberries. The order of the strawberries in a pair is randomized. So to describe the strawberry and environment more precisely, some parameters are considered like distance parameters, the visibility parameters, and the parameters about space around the target. So the parameters for the 2 strawberries in a pair are placed together in a factor later, and the factor is labeled depending on the ordering of the 2 strawberries. A basic neural network with 2 fully connected hidden layers was trained on data with such format. When using this neural network for classification, feed a parameter a factor generated by 2 strawberries into it, and the order of the 2 strawberries will then be calculated according to the output. So applying this to all the red strawberries in a certain map, there will be a possible sequence for having all of them in a preferred order. So this is the information on the data sets collected from the game until April this year. So it's shown in the table above. So we consider data from easy mode game that had just 2 or 3 strawberries as separated from data generated from other easy mode games. The accuracy of the neural network chain on each data set is shown in the table below. So we took like similar sized samples from each data set and chain and tested them. So comparing different rows, it is noticeable that the 2 strawberry data set is the best choice to train a robust classifier. There's also a clear difference between easy mode results and hard mode results, as a classifier trained on the 2 strawberry work very differently on hard mode dataset comparing with ones working on other easy mode datasets. So we also tested this sorting method on a small number of examples as a pilot study. So here we used A* for path planning, and then a heuristic method from near to far and left to right, and our neural network sequence sorting method were both applied to target sorting and then compared. So they are tested on 133 groups of data following the distribution of our strawberry fruit model. As a result, our neural network sequence sorting method works worse only in 27% of the cases than this simple heuristic method. So here are two examples showing the path planned. So this plot shows the basic idea about how we train the classifier as a summary. The experiment suggests that human harvesting follows a pattern that can be retrieved from data collected so far. And when tested on some examples as a pilot study, our sequence sorting method works fine, but still have some space for improvements for sure. And we plan to use this in future research on task allocation in harvesting. And this sequence sorting pattern will be compared with other sequence sorting algorithms later. Okay, so that's for me. I hope you find this piece of work interesting. And if you are interested in trying the video game out yourself, you can find it following this link. Okay, thank you.
Thank you very much, Zuling. Any questions for Zuling? Okay, Zuling, I have a question for you. So you said in your comparison you had that baseline A star, right? The heuristic, you said.
The A star is for used to plan the path. So the baseline is the simple heuristic method.
Okay, so that is my question. It wasn't clear to me what you meant by that. So how do you decide on the next strawberry to pick in that case?
So basically use the neural network sorting method on all the strawberry pairs in a strawberry map. So comparing each pair, so for each pair we have a preferred strawberry than the other strawberry, like comparing the preferred strawberry to other strawberries one by one, like the bubble sorting method. So we will have a sequence planned.
Okay, I understand. Thank you. Saria, please go ahead.
Yeah, hi Zuling. Thanks for your talk. So my question is related to do you think in the game you place the gripper, you constrain the gripper to go on the top of the fruit?
Yeah.
Do you think if you don't put that constraint on the person who conduct that game, do you think the results can change somehow when you compare the neural network to another heuristic method? Do you think that constraint can affect your results?
I think that might affect the results. I haven't tried it. But when I was playing the game myself, I will consider like where is the right place to put the gripper. So if the shape of the gripper change or the approaching point or the picking point changes, the result I think might change as well.
Okay, so it needs to be a bit generalized.
Yeah.
Any orientation, if we want to rely on human demonstration, let's say.
I think so.
Okay, thank you.
Thank you.
Amir, please.
Thanks, Mehmet. Thanks, Zuling, for the talk. It was interesting. So to what extent do you think that this game helps bringing robotic technology to the field and pick strawberries? Why not just collecting some videos of pickers in the field and then try to extract information from the real pickers practicing the picking actions?
So first of all, so when taking a video of a picker, we don't know what exactly they're looking at. So at their viewpoint, how the obstacles affecting the target, like from the camera, the obstacles might not be the real obstacles like on the path. And the second thing is that we might need like a large number of data to do the training and testing. So taking a video might not be that easy, and we need to label all the data from a video later.
Mm-hmm.
So yeah.
Okay, and how your game and the data that you collect using your game help bringing the robotic technology in the field and help the robot to decide how to pick? How transferable is this knowledge to the real field?
So the model is using the distribution of the real strawberry plant. So when applying to the farm, like I think just need to scale the data sets a little bit according to the real size of the strawberry plant, but the model itself, I think, should be able to be useful.
Okay, thank you very much, Zhuoling.
Thank you.
Yes.
Thank you, Amir. Thank you, Zhuoling, again for your talk.
Thank you.
Our next speaker is Lewis Anderson. Lewis, you are here, right? Yeah. Hello. So Lewis is the co-founder and CEO of TrapTig. He's coming from the company TrapTig, which he started to solve a critical labor shortage in the food production system. And they're using giant robots. And I'm looking forward to see some videos of those giant robots. Currently, $200 billion worth of produce is picked by hand, but a large percentage is wasted because not enough people are available to pick it. TrapTig's giant robots are saving the world's food production system by doing the work people don't want to do. Before starting TrapTig, Lewis built software for PowerPoint at Microsoft, which has been used by hundreds of millions of users. Indeed, he started his career building autonomous airplanes and studying computer science at UC San Diego. Lewis, please go ahead.
Awesome, thank you. And you can hear me?
Yes.
Okay, cool. Awesome. So I'm Lewis Anderson. I'm CEO of TrapTig, and definitely thanks for the opportunity to talk here. So I'm going to start with an intro about TrapTig, and then I'll go into some technical details. So 200 years ago, we picked wheat by hand. It's a bunch of people out in the field with hand tools doing things manually. And nowadays, we do that with giant combines. So these machines harvest very quickly, efficiently, and at enormous scale. But they really lack the delicacy and the precision necessary to harvest most fruits and vegetables. So as a result, more than $200 billion worth of fruits and vegetables every year are still picked by hand. Why is that a problem? Let's take strawberry picking. So first of all, we have fruit rotting in the field because there's not enough people available to pick it. And at the same time, the labor that is available is super expensive. So it costs about $20,000 an acre. That's about 35 cents a pound, just for the manual labor for harvest. And that labor is getting more expensive and more scarce due to an aging workforce around the world, national political dynamics, and California labor laws. So introducing TrapTig. Our robots are saving the world's food production system by doing the work people don't want to do. So we're watching an older video first, just to give you a sense for what it looks like to pick berries in a farm. In terms of kind of our long-term plan, our master plan basically is to start off by first getting $3 billion in revenue by picking strawberries, then get $20 billion in revenue by picking the other fruits and vegetables that are currently picked by hand, and then go after the $200 billion in crop value by automating and improving remaining activities. And we'll be deploying commercially in the next few months. And I wanted to mention one thing about our gripper, which is that the patented gripper you saw in this video just now, which delicately grabs the skin of the fruit, would work really well for raspberries and things like that. But we found that it's actually not precise enough to pick berries in clusters. So we ended up making a big change. So our new gripper actually grabs the stem of the berry, and it grabs it hard enough to crush it, so that when we pull away from the plant, the stem breaks. And this allows us to pick actually most kinds of fruit and vegetables with the exact same gripper. And it'd be very easy to substitute a larger cutter for larger foods. So yeah, let's dive into some more technical details. So first of all, farms are pretty decent semi-structured environments for robots in general. So we see that plants grow in consistent raised beds. There's much looser safety and regulatory requirements compared to a lot of other industries. And we also see that growers are really recognizing the urgency of their need to automate this work. And as a result, they're extremely supportive of our efforts, which, that combined with the technical aspects really makes this problem tractable. There are also some unique benefits of solving robotics challenges in our environment compared to, I think, a lot of typical research environments. So first of all, we've been deployed continuously in the real world for years, and we're generating tons of data from the machines that we have. Our machines are out in the field picking all day, every day. And that means that when we make code changes, we can test the results on a real world system in the same day with no or minimal engineer effort. So there are some difficult aspects to this challenge, of course. So we see that we have to operate in a very harsh environment. So there's farm dust, there's rain, there's wind, there's sun, there's vibrations, other factors. We also have really serious reliability requirements. So in order to really deploy this at scale, you need to be operating for 20+ hours a day, 6 days a week, year round. So you need a very reliable machine. And of course, you need substantial scale in order for the economics to work. You just need a very large machine. So what we've done is we've developed a platform with 8 robot arms for massive scale. It has tons of computing power on board, just mostly to make our lives easier on the software side. We have Charuco boards permanently mounted to the machine, so we can do easy real-time calibration. So we can have a robot arm stop and recalibrate itself while the other arms are picking. We have strobe lights on the end of the gripper, which these flashes of light for the cameras give us really good image quality, even in direct sunlight, even while moving. And finally, our platform is inspired by construction, other agriculture equipment, factory robotics, and even automotive work. We haven't publicly shown the full platform, though you'll see hints of it in some of the pictures and video, including in my background. So the stack we use, we have powerful Linux desktop computers and big graphics cards. We use Python and C++. We're using ROS, TensorFlow, OpenCV, and a lot of the other standard libraries you'd expect. So this is a video of what it looks like to pick a berry by grabbing the stem. So the next major challenge for us really is to perceive the scene. And so the tricky part here is if we look at this very crowded environment, you can only see a portion of each berry, stem, and plant. And you must, based on this image, you must identify which of the fruit are ripe and where their stems are, so you can go pick them. Also, the plants tend to change throughout the season. So the plants will grow 10x in size from beginning to end. The colors will change. They'll be different in different parts of the farm. They'll be different between farms, and lots of other things. So lots of challenges here. We solved this with a combination of neural networks and traditional methods. And we're hoping to publish something on this sometime soon. The next challenge is for 3D accuracy. So we really need to determine the position of the stem in 3 dimensions. And we need to place an end effector on that stem with about 3 mm precision in order for us to get the target fruit without missing or disturbing the nearby fruit. So you can see in this one, we need to be very accurate to grab that stem without, hitting one of the berries nearby. So, of course, we have to handle errors in lots of different places. We have to handle a camera calibration error in the robot arms positioning, camera mounts, the lenses deteriorate, we have stereo matching error, perception error, all kinds of things. Our solution here basically is we've developed a custom color stereo camera. We do the stereo matching on our onboard computers. We do an eye-in-hand calibration process. One of the cool things here is that we can run that automatically on a robot arm while the other arms are actually picking berries. We've also had pretty good luck with open source tools in the kind of calibration and stereo matching error. I wouldn't say we've had to solve any single problem that's super hard, but instead we really need system level excellence here. We have to nail every level of the error stack in order to achieve good performance. So this is really more of a system level challenge than a challenge in any one component, I would say. And finally, we have to do all this from a platform that is moving through dirt on big pneumatic wheels. So it's not all that stable. We also need to do it quickly. So each robot arm must pick a berry every few seconds in order for the system to be economically successful. Because of course, that economic success is a requirement for deploying widely across the world and having that big impact. We also are seeing that the time spent per pick is dominated by robot arm motion. So the computation itself must be very fast. The next challenge that we have solved is really one of obstacle avoidance. So we have to push our end effector through a bunch of soft obstacles, stems and leaves, in order to pick a berry. It's usually okay to push through those obstacles. You push a gripper tip, through a leaf to get to the stem. But other times you want to avoid that. So like if you have a bunch of wires in the back of the gripper and you're pushing those wires through the plants, they tend to get snagged and broken, so you don't do that. And there are also hard obstacles that we need to avoid. So in this image, you can see this big sprinkler dominating the image. These often tend to be unexpected and fairly random. There are also a bunch of predictable hard obstacles, like the shape of the bed itself. Though even those predictable obstacles tend to vary quite a bit. We see that our platform wiggles around, so information about obstacles tends to become out of date pretty quickly. They're also just not that regular. So here's kind of an example of how our system detects that sprinkler, puts that cylinder around it. The way we've done this is really, we've come up with some ways to aggregate 3D data across many frames in a format that's highly efficient to use. And then we can run analysis on that aggregated data to detect parameterized objects. So a parameterized object like a bed that has kind of a consistent shape, stems, which are very narrow cylinders, berries, etc. We can also use that aggregated data for very straightforward collision detection. And then here's kind of a snippet of our metrics. We have pretty detailed metrics about how the system performs. And kind of looking forward, we have the capability here to really radically improve the way food is grown. So we can make decisions at the plant level and individual fruit level rather than the field level. We can do careful manipulation that allows us to grow much tastier, more delicate, healthier food much more efficiently. We can do pruning, pest care, we can minimize fertilizer usage, we can track plant health, we can allow much more delicate and tastier varieties of plants. There's a whole bunch of things we can do using robots to really radically improve the way food is grown. And in the meantime, we get to eat lots of tasty berries, which is awesome. So yeah, we've solved some tough and exciting problems so far, and we definitely have more to go. So if you'd like to help, definitely shoot me a message at lewis@traptic.com. Thanks, and I will take questions now.
Thank you, Lewis. Any questions for Lewis? Mintron, please go ahead.
Thank you. Very, very interesting. A very giant robot. So do you think that this robot arm is too big to pick a small fruit, like so small fruit?
What we see is that the stem that we're grabbing is super skinny. It's like 1 or 2 millimeters thick. So we can have a giant robot pick a very small object. The one constraint is you need to be able to get the robot arm near the plant. So you need enough space between the rows of plants or above them to get your platform close to the plant. So in our case, we're able to drive our platform over the field. The robot arms can reach the berries and pick them, even though they're quite large. So most fruits and vegetables are structured in such a way where you can get a machine to the plants.
But what do you think that use like a smaller arm, like a smaller robot arm, is that better or?
So the two main factors here, I think, are we need to have enough payload capacity on the end of the robot arm for our gripper plus sensor package. So that's gripper and 2 or more cameras and strobes, and those are a bit heavy. And then we also need really good cycle time. So you need to be able to move that payload around quite quickly. And so typically you need fairly large robot arms in order to move this payload around at the cycle time requirements that we have.
So how much payload currently of this kind of your grippers, your camera, and I also see there's some light source, so illumination stuff. So how much heavy all of this stuff together?
It's probably 1 to 2 kilograms right now. And I think long term we could lighten that up quite a bit. But for now, it's very convenient to have that weight capacity. And the robot arm we're using can handle like 3 to 5 times that, so that that makes our life a lot easier. I think one of the things we've seen is that doing this at scale is so challenging that anywhere you can like make your life easier, whether that's a big robot arm so you can have an extra large gripper package, or like tons of extra computing power so that you don't have to make your software as efficient. Anywhere you can do that is, I think, super worth it.
Okay,
Thank you.
Thank you.
Saria, please go ahead.
Yes, thank you. Hi, Louis, and thanks for your talk. So my question is about, you mentioned that the robot needs to avoid static obstacles and soft obstacles. Can I ask what, in terms of planning in real time in the field, what do you use in order to overcome or to avoid obstacles in the field?
Yeah, so we definitely do all of it in real time. Of course, we don't know where the obstacles are in advance. So on the perception side, we have those ways of aggregating the 3D data into a format that's really efficient for us to use. So we're able to do basically constant time lookup on whether there are obstacles in certain places or not. And in terms of planning around that, like planning using that information, it's primarily custom code that we're using to do that planning. Using of course some standard open source things. So I would say the perception and the finding ways to work with the perceived data efficiently is the biggest challenge. And once we solved that, doing the planning on that data was easier. Does that answer your question?
Yeah, thank you.
Thank you, Saria. Willow Mendel, please.
Hey, Lewis. Yeah, I was just wondering about what was the reasoning behind using a 6 degree of freedom robot instead of a Cartesian robot or something like that?
Yeah, we found that one of the reasons is that you have berries, the bed is shaped kind of like this, and you have berries that grow on the top of the bed, and you have berries that kind of hang down to the side of the bed. And with a 4 degree freedom arm, if you have your gripper fixed a certain angle, it's pretty challenging to pick all the berries. So you kind of have to fix it at a certain angle. And even with multiple arms, you have to say that, some grippers do bed berries and others do, furrow berries. Whereas with a 6 degree freedom arm, you can kind of do all of it at the same time. We also saw that the 6 degree freedom arms had pretty nice workspaces. They're much larger workspaces, especially in the Z direction than a lot of the 4-axis arms that we used. So we used to use a 4 degree freedom delta robot, but that kind of had a very limited workspace in the Z direction, which actually made it pretty tricky.
Okay, thanks, Lewis.
Thank you very much, Lewis, again. It was great listening to your talk. Amir, do you have a question?
Yes, very quick one. Okay. Luis, very interesting. It is very, very nice to hear about your company and your work. How far is this from commercially viable solution to strawberry picking?
We're going to be deploying commercially in a few months, so it's basically there.
And do you have, in terms of the business, so how you compare the cost against the human pickers? Is it kind of justifying the kind of business plan for the growers to just ask you to develop this, to provide this picking service to farmers? Or?
Yeah, that's a great question, because oftentimes the business model and kind of the deployment plan is as much a barrier as any technical things when it comes to deploying robots. So we're going to run this as a service. So basically, we go out and pick berries, and the growers will pay us a cost per pound to pick them, just similar to how they're paying for their existing solutions today. We also see that there's such a severe labor shortage that, you know, when we go in and if we charge the same amount as what they're paying people today, or even a little more, that they're more than willing to pay that. So we'll go in and we'll charge about the same as what they're paying people, kind of on a similar schedule. And the service model makes that very easy because they don't need to pay this big amount of money up front. The final thing is, you know, I think for quite a long time, the goal of this will really be to augment the existing human workforce. So you have this combination human-machine solution that is able to harvest all the berries across the industry. So that'll be, that also is really helpful for deploying effectively.
Thank you very much. Very exciting.
Yeah, thank you very much, Lewis. Thank you, Emir. And now we are into another session. Am I right, Saria and Tommaso? Yes, I'm right. Okay, I will be handing off to Emir then, I think.
Yes, so thanks, Mehmet. And I'm also excited to, now we have this Spotlight talks, which are submitted papers. It may last for 12 minutes. After that, we have 5 minutes presentation by the sponsor of the Best Paper Award of this workshop, which is Whaley, and we will listen to their kind of services. And after that, we have the panel discussion. I'm very keen to listen to Robert and also Luis about how they see the future of agri-food manipulation and robotics. As we have seen, they are developing kind of platform as a service. So this is kind of very interesting for me. I'm going to share my screen and start the talks on the papers. Can you see my screen, guys?
We can, yes.
Okay, excellent. So I would like to ask all the presenter of the papers, please just be mindful of the time. You have 1 minute for each paper. I saw some of you send me several slides, but please try to keep in the time, keep yourself in time so that we are having time for the panel discussion. So the first paper, the first Spotlight talk is by Alejandro, which is learning to pick apples using an apple proxy. Please be ready to turn on your camera and your microphone to talk over your slides. Go ahead.
Yeah, hi, I am Alejandro. We're working on learning to pick apples using an apple proxy. Next slide, please. So we choose apples because it's one of the most consumed fruits within the Americas. Plus, it has some similarities with other fruits. And we wanted to see how to pick apples, but from a physical proxy rather than from simulations. Next slide. We are doing it with a simulated environment. In this case, we reproduce the stem, the apple, with 3D printed parts, which have the rotational degrees of freedom. Next slide, please. We also rotate the branch where the apples and the stem are located at. And next slide. We implemented a UR5 robotic manipulator with a 2-finger robotic gripper, and we approached the apple from 3 different positions by adding noise from ±5, ±10, and ±15 degrees of noise. Next slide. And these are the results that we obtained. So from the top row, we have the successful picks, whereas in the bottom row, we had the unsuccessful ones. So we are, with this, we see the potential of our apple proxy to detect, to tell from good picks from bad apple picks, and we're looking forward to implement more variables into this so we can do machine learning. Next slide. Yeah, so we obtain a similar behavior from real apple orchards. We see the apple or our apple proxy is promising for detecting, and yeah, thank you.
Thanks, Alejandro.
Sure.
We will have 5 minutes for question and answer after all the paper presentations. And also, The nominations and the award announcement will be at the end of panel discussion. Thanks, Alejandro.
Okay, thank you.
Will be, this is okay. The next talk will be by Vishnu. If you are here, please turn on the camera and mic to talk over your slide. All right, so if Vishnu is not here, we can move on. The talk is about comparison between manual and robotic selective harvesting. The third talk is by Marcella, and it is on robotic harvesting from peppers to berries. Marcella.
Hi.
Hey, please turn on camera and speak over your slides. Go ahead.
So hi everyone, my name is Marcela. I'm from the University of Zagreb in Croatia. And here we're presenting some early work that we're doing as a part of the Specularia project, where we're developing robotic solutions for indoor agriculture in general. And in this work, we're focusing on harvesting, and we're analyzing if one solution that we developed for one crop can be adapted for another one. Can you change the slide, please? So in particular, we're building upon what we've learned with sweet peppers and trying to develop a solution for strawberries. And here you can see that we're focusing mostly on the perception method at the moment. Basically, we're developing synthetic data sets for training methods for detection of the fruit that we're picking. We're also working on other parts of this problem, but for more details, we can talk later, or you can see the abstract that we've submitted here. Thanks.
Thank you, Marcella. And this is the team. The next talk is about strawberry harvesting. Willow.
Hey guys, I'm Willow. This was a little investigation to modeling soft fruit clusters for controlled harvesting. The problem being that we can't just apply obstacle avoidance here, and that we have to actually push strawberries out of the way to reach the target strawberry. Next slide. So we're approaching this from the control side, from a model predictive control standpoint. And in this work, we're focusing on the actual prediction of the strawberry plant when being pushed by a robot. So we collected, oh, next slide, sorry. So we collected 500 interactions between the robot and randomly generated strawberries, and we trained a video prediction tool, which we adjusted slightly for 3D trajectories instead of 2D, called convolutional dynamic neural advection. And as you can see, although the prediction contains a fair bit of noise, the overall motion of the strawberry is captured by the model. So now we have a promising prediction platform for us to build on and push towards prediction of more and more complex strawberry clusters with the view of harvesting them for model predictive control systems. Thanks for listening.
Thank you, Willow. The talk 5 is by Alexander, executing monitoring for robotic pruning using force feedback. Alexander.
Yep. Hello. Hey, everyone. I'm Alex. And so my work focuses on dormant pruning, which is one of the costliest activities around fruit production besides actually picking the fruit itself. And one reason that autonomous pruning is so challenging for robots is that there's very high precision required to execute these cuts. And so for our experiment, we wanted to take a look at how we could use force feedback to tell if the robot was succeeding at cutting or not. And to do this, we built a set of mock cutters and a mock cherry tree, shown at the bottom left. And we collected force data by moving the cutters towards the target branches. And after we labeled the force data, we trained an LSTM neural network system to take in this data and output a belief of success or failure. And ultimately, our system was able to learn meaningful differences in the force profiles between successes and failures. And it achieved a relatively high classification accuracy of about 80%. So our future work would be to gather more data and learn how to combine this force feedback with control to actually increase our pruning success rate. Thank you.
Thanks, Alexander. The next talk, talk number 6, is by Qingyu, an end-to-end deep learning stereo matching method for robotic leaf sampling. Qingyu. Koingyu, are you available here? All right. If you're not here, we can move to the next slide. Next talk. Oh, it was interesting. All right. So the talk number 7 is by Nicolas and teeth pose estimation via RGBD segmentation for automated milking.
Yeah, actually, it's Giovanni Toffetti from Zurich University of Applied Science. Hi, everybody. This is joint work with the colleagues that you see there. Next slide, please.
Yes.
So we're building a robot for automated milking for the Swiss market, because the Swiss market is slightly different than how milking happens in industrial farming. And we are building a cheaper, smaller robot that can be sold on the Swiss market and modernizing the technology that has been used there. Next slide, please. So we're using RGBD cameras to find the pose of the teats for automated attachment to then pump the milk of the cows. If you're interested in the evaluation of some of the commercial cameras, you can read them in the paper. Next slide. And these are some of the results. You can go to the next slide. We evaluated the quality of the pose estimation of the teats by using a COVID-compliant plastic cows. Plastic cow, we achieved quite good precision, which you can see in the next slide. And we will update you with better results on real cows soon, hopefully. Can you show the next slides? These are just the results. Yeah, these are the errors we're getting around a couple of millimeters in average. Thank you for the attention.
Thanks, Giorgio. Thank you very much. The talk number 8 is robotic perception, agri-food manipulation and review. Jack.
Can you hear me?
Yes, go ahead, please.
Awesome. Okay, hi everyone. So our review paper was on robotic perception for agri-food manipulation. And next slide, please. So some of the key takeaways are convolutional models are increasingly ubiquitous these days, as most of you probably expect. But this is leading to issues around data availability. There's just a lot of crops, a lot of different issues that require different data sets, and it's very laborious to actually build these. So there's quite a few different attempts now to actually alleviate these issues. The most interesting were data synthesis using GANs, and also unsupervised pre-training on different data sets. And then just the last point that I'll make is there's actually quite a need for lighter and faster models so we can see deployment on robotic hardware in the field, because a lot of these models are just running on some big cloud server somewhere on massive GPUs. Thanks for listening.
Thanks, Jack. Talk number 9 is by Alessandro.
Yes, hello. Can you hear me?
Yes, please go ahead.
Thank you. This is Alessandro Di Fava from Robotics. We are one of the leading companies in Europe of service robotics. And in this work, we presented our approach to bring robotics from labs to agriculture field. This is why, because I mean, we know that nowadays the population in the world is growing, so there is an increasing of demand for food. And so technology, and especially when I say technology, I mean robotics, needs to help to improve the food production and processing. Next slide, please. In this direction, we presented a project where we are involved in a European project that aims to take over all the tiring and repetitive tasks that comes inside the agriculture. In this special project, we are managing to show our robots to do some harvesting, pruning of grapes in a vineyard. We use a mobile manipulator robot to trying to have a team of robot plus people doing some, I mean, 2 robots, one for farming to do this harvesting, pruning, and the other robot for logistic, together working collaboratively in some with other farm workers. But the project just started, so we are just in the beginning of this work. Thank you.
And Alessandro, is it a Research Innovation Action Project or Innovation Action Project? Can it be?
A Research Innovation Action Project.
Okay, okay. Thank you. Thank you very much.
You're welcome.
And the next talk, talk number 10, is state estimation of underactuated gripper during robotic food picking by Miranda. Miranda?
Hello, my name is Miranda Kravitz. I'm a first-year PhD student at Oregon State University in the Intelligent Machines and Materials Lab. Next slide, please. Apple orchards are unstructured, cluttered outdoor environments, which makes robotic grasping that much harder. Underactuated grippers are uniquely promising for this type of challenge thanks to their ability to compensate for localization error during grasping and their robustness to collision. However, since the pose of an underactuated gripper depends on its interaction with the environment, state estimation and control are particularly difficult. To address this problem, we have developed a simple method of state estimation using off-the-shelf inertial measurement units and a simple kinematic model of a robotic gripper. We hope to use this method to evaluate whether a grasp during an apple picking attempt has been obstructed and should be replanned. Next slide, please. Thank you for listening, and if,
Oh, I'm sorry, I guess that's correct. I'm very sorry, this is my mistake. Anyway. That's good. Thank you very much. And we can move to the next talk. Thank you. I'm sorry for this.
It's all right.
The talk number 12 and the final talk that we have is on robotic manipulator in agriculture, another review paper by Harry Rogers. Harry? Okay, Harry is not available here. Am I missing any other talks? These are the talks that I received. So if I'm missing anything and you are available to talk over your paper, please let me know. Otherwise,
yeah. Hi, this is Vishnu. Yeah, I have.
Oh, Vishnu, I guess you were the
second one. Yeah.
Yeah. Okay. Okay, go ahead.
Yeah.
Go ahead, Vishnu.
Yeah. So, hi, this is Vishnu. I'm a PhD student at University of Lingen. I'm working on end effector designs for strawberry harvesting. So that is the basis of the extended abstract that I've submitted. So basically, what we have done is like so when we have closely analyzed different end effectors available for selective harvesting for robots, we have identified certain shortcomings which actually cause some of the problem of the total robotic system. So what we have done is like we are just closely looking at how a human picked the strawberry and how certain clues from that can be used for improving the features of the end effectors, like to improve the performance of the end effectors while dealing with clusters and preserving the quality of the fruit during the attachment, detachment, and the transportation phase of the picking action. So these are some of the key constraints that we are looking at when we are designing an end effector. So since this problems is not just because of the end effector, but as a system as a whole, but we believe that certain modification at the end effector level can improve the total performance of the robot. So we'll be more looking into incorporating like multiple degree of freedom end effectors with tactile sensing for picking the fruits that is in a dense cluster, and also looking at coming up with a new methodology of fruit transport action after picking, so which actually reduce the total cycle time, and also the chances of let's say when we actually use the same tool for picking the strawberry, there's a chance of disease of transfer from one plant to another. So we're thinking how to do such kind of sanitation task in picking action when a robot perform the selective. So these are some of the things that we have discussed in the paper, and we will share the much updated results soon once you have finished this. Yeah, thank you.
Thank you, Vishnu. If everybody covered his and
sorry.
Anybody else?
Yeah, so I think I can represent Qinyu.
Okay,
number
cool.
6. Yeah.
Okay, good.
So
go ahead.
Okay. So can you go to the next slide? So our topic is breeding end-to-end deep learning stereo matching method for robotic leaf sampling. So currently, the breeding plays an important role in improving food yield and solving global farming problems. Living sampling is one of the primary tasks of molecular breeding for DNA marker and detection, which is highly repetitive and labor intensive. Thus, we develop automated leaf sampling robot to replace the manual labeling and boost the breeding process. The main purpose of this study is to develop a visual perception system for sampling the robot and provide 3D information of target groups. So we using end-to-end PSM-led deep learning method to replace the stereo vision system, which can obtain a very high position accuracy to provide with a low cost to provide for the robot perception system. Yeah.
Thank you. Thank you very much. And now we can move to the presentation of our sponsor for the Best Paper Awards, and that's yeah, okay. So Babak Mostagachi is the editor of Advanced Intelligence System journal from the Wiley family, and I invite him to give a very short introduction to their activity. Babak.
Hi, can you see my slides?
Not yet.
I guess they are. Oh, okay, so perfect. So hello everybody, and many thanks to the organizers for giving me this opportunity today to introduce our journals to this community. I try to keep my presentation very short. So my name is Babak Mostagachi, as Amir mentioned. So I'm working for Wiley. I'm editor of a number of journals at Wiley, including Advanced Materials and Advanced Intelligence Systems. As a matter of fact, Advanced Intelligence System, that is the main sponsor today, is a member of a group of very prestigious journals. We call them Advanced Family of Journals. The top journal is Advanced Materials. As a matter of fact, the journals are mostly known in chemistry, physics, and materials science communities. Advanced Materials is one of the maybe most prestigious journals in the natural sciences communities with an impact factor around 27. You can see in the picture there are several sister journals, just I mentioned some of them here, but in the last few years we have started to expand the scope of our journals to some other fields, sustainability, to general scope science like advanced science, for example. They just publish everything. Advanced theory and simulation focused on theoretical results, theoretical research. So we have now some journals beyond material science. Advanced Intelligence System is one of the youngest members in this community. Its scope covers interdisciplinary research related to intelligence systems, including topics like artificial intelligence and machine learning, robotics. Sorry, I guess the slides are not. Can you see the slides?
Yes. Sorry, yeah.
Yes, go ahead.
So the topics include artificial intelligence, machine learning, neuromorphic computing, robotics, quantum computing, and all different interdisciplinary topics. So we have, in order to be in contact with our global readership, we have editors in different countries, even different continents. I can say, and so like many other journals, or like maybe some journals, the journal enjoys an in-house editorial system. It means that all of the editors, they are full employees of the company. So it has pros and cons, but it works for our journal so far. So the journal enjoys having a very top editorial advisory board, although the journal is very young. As a matter of fact, we recently celebrated the 2nd anniversary of the journal. But anyway, we have published several invited-only special issues on topics like soft robotics, space robotics, haptics, and many other things. We have, as a matter of fact, we have, for example, one special issue on neuromorphic computing or modern computing approaches that is going to start soon. And one very interesting aspect of the journal is our collaboration with Autoria, enabling authors to publish interactive content alongside their papers. By interactive content, I mean they can just publish data-driven figures or executable codes, Jupyter notebooks, 3D models like 3D CAD models, for example, or whatever. So the system is quite versatile. And then we always try to increase the visibility, enhance the visibility of the papers. We have an editor's choice virtual issue, highlight the best papers in the journal. We normally create monthly videos highlighting the best papers in each issue. And as I mentioned, we are highlighting the papers with interactive content, both on Wiley Online Library and also on Autoria collection. So they are getting highlighted in different places. Before concluding my talk, I want to also draw your attention to another robotics-related journal at Wiley, Journal of Field Robotics. Probably you're familiar because the topic of this workshop is also related. The journal has been out there for several decades, I would say, so it's quite well known in the community. If you're interested, please refer to the journal's web page. And by this, I would like to thank you for your attention, and please feel free to contact me at any time if you have any questions. Thank you.
Thanks, Babak. Thank you very much for the nice introduction to your editorial services. And now, this journal supported the Best Paper Award, and we will announce at the end of the panel discussion. Now I hand over to Saria to start the panel discussion without any break.
Without any break.
I don't know. Mehmet is the best expert to advise us if we need any break or not.
I don't know. I think we can continue, but like, you know, it is, if it has been like, you know, it has been a long time since we started, so I'm sure people are tired as well. Though my preference would be to finish, like do it and finish it instead of taking a break now. But yeah, if anyone thinks otherwise, we are happy to hear, I guess.
Yeah, I guess what that was good, Mehmet. We happy?
Yeah.
Okay.
That's fine. So
is there any vote here? We could vote for this. That would be nice.
Paul, yeah. So from all the speakers that are still with us, first, thank you. And we would like to ask you if you want to unmute yourself or the microphone, turn it on. And I would like to start by addressing a generic question to Louis. So Louis, based on, I will go from the field towards the lab now. So beginning from the field, in terms of 3 factors that are important in the field. One is the time of operation. Second is the success of a task. And third is the food safety. So in order to cope with those basic and essential requirements in the field, in your opinion, to which extent the challenges that you saw so far in, let's say, the harvesting task have been able to be approached or best solved with the current technologies that are presented in the literature or in the state of the art? So to which extent they have been met, those requirements so far, in order to cope with the challenges that you saw in the field? And what are the remaining requirements that that we need, or the researcher or the engineers needs to work on?
Yeah, that's a great question. So going backwards, in terms of food safety, I would say the state of the art is there. So like very similar tasks have been done both in fields and in food processing facilities for a long time. So we basically just leverage all the existing state of the art and existing best practices for food safety. In terms of speed of operation, and what was the other part?
The time of operation and this task success?
Task success. Yeah, so for task success, I think agriculture and like picking food is pretty nice because the success requirements are a lot lower than a lot of other industries. So if you're doing a self-driving car, obviously you need a very high success rate because you don't want to like crash cars into people. But if you like smash a fruit once in a while, it's okay. So it's like not such a big deal. I would say for the most part, you know, most of the state-of-the-art algorithms out there do pretty good in that area. The you know, speed of operation or the cycle time requirements, I think that's pretty tricky. Some areas of the state-of-the-art, like modern like neural networks for doing detection and videos, those are quite fast. Those are very good, so we're happy there. But a lot of the state-of-the-art like planning approaches can be very slow in some cases. So we found some challenges with speed in those areas in terms of, yeah. And then the final thing is, I would say the biggest challenge we've had is really whether a lot of these state-of-the-art technologies are robust enough to be deployed at scale. So there's a lot of things that work really well when you're, you know, one person is running it, like in the lab. But if you try to deploy it on a machine with a bunch of robot arms that's operating, you know, 24 hours a day, the reliability can be, you know, quite challenging. So I would say kind of that reliability and that like production readiness is probably the biggest challenge with a lot of these state-of-the-art robotics things.
Thank you. Yeah, and so what's about, so this is related to the scalability of the technologies that are developed in the research to go to the field, right? So the major problem is to scale whatever is developed to be reliable and robust in the field.
Exactly, yeah.
And maybe Lorenzo, Dr. Lorenzo. So for example, we saw the challenge in the field of the occlusions in clusters. What can the perception or multimodal perception can enhance in that for that challenging task? Because I think it still lacks some advancements or some success, and it can increase by, like, the success rate of achieving the task can be enhanced a lot by using multimodal perception. What's your opinion regarding that?
Yeah, I mean, I agree. I mean, to be honest, of course, my experience in the field, meaning the actual crops, it's zero. So I don't have any. But I believe that I see that most of, even during this workshop, many of the technology that we have seen, they mainly rely on computer vision. And in my opinion, yes, adding tactile sensing could help to, especially in those cases where you have occlusions. Not just in manipulation of fruits, but in general in robotic manipulation. So we know this from other examples also in industry and manufacturing. So yeah, general answers is yes. In terms of why why, for example, tactile has not been used much in the deployment, I think it's related with the fact that the technologies are still not as developed as computer vision, but hopefully there will be space for it in the future. I think so.
Thank you. Yeah.
I was wondering to see if, because you have listened to others talk, so I saw very interesting talk by Robert and very exciting talk by Luis and also Lorenzo. You were covering more academic aspects of manipulation. So how you challenge each other? So from industrial application of the robotics in agri-food domain, and from the perspective of developing technologies in the lab, what is the gap between these two? So what we need to push in order to make the technology transfers from lab into the field? Robert, I guess you're the best candidate to start. You both, right?
Yeah, so I mean, in theory, to get the system to work is like, as a researcher, you always like, okay, this is a solved problem. I can get this to work in a single demo and It can pick up my food, may it be outside or maybe in our case it was inside in the kitchen. But once you actually have to bring it to a customer's hands and like closing this last 20% gap that you think is just the last 20% of functionality, but as we all know, in reality, it's like 80 to 90% of the work. And so, to be quite honest, this is a very time-consuming process, very resources-intensive, no matter like if it's autonomous driving, if it's DeXi's Alfred robot in the kitchen, or any other robot that was presented today. You always have all of these extra challenges that as a roboticist in research seem completely boring. Boring in the sense of you have to provide a user interface, you have to, I'm hearing a lot of noise right now, not sure what's going on.
Okay, I guess now it's fine.
Okay, thank you. So what I found for DeXi, for us specifically, was that we were trying to take this idea of manipulating food in a bin. That's basically what it was. We want to say the structuredness in our problem is put food in a bin instead of having it on a table or having it somewhere else. We have it in a bin. And then we say we have the human's help of doing all the food preparation. So really, we just broke it down to this one problem of manipulating the right amount of food, just the portion control. And even doing that reliably up to the level of what the customer wants is incredibly challenging, because you basically need to be able to put this system into someone else's kitchen and it needs to work so that they don't throw it back at you and say, hey, I'm just going to hire a more reliable human worker. So you're actually just competing against the human in this case. This is just what it is. It sounds scary. It sounds also a bit stupid, but that's really what you're doing. Like you're trying to do something which a human can do very easily, and we're nowhere near to doing it as easily as a human can do it. But so we're taking a subpart of this problem, and then we found out that, well, if we really nicely confine it and we fix this problem well and we find the right algorithms to do it and we put all of the other safeguards into place so it can sit in this kitchen and no other person comes in, we can make it happen. But then still they told us it has not a nice user interface. It's not washable. It's not this, it's not that. So all of these other requirements come in. And so beginning you think you can make this happen in a year or two, and suddenly you're facing like these many years of timeline in where you can actually make something scalable to the level of, how say, hundreds of McDonald's or hundreds of other like shops where you would deploy it into. Sorry, this was probably a very long-winded answer to your question, but I think there is so much that goes into making a product that has nothing to do with robotics in the end. It has to do with good product developments that takes up all of the effort.
Thanks, Robert. And who wants to challenge this answer? Mehmet, you are working on clutter manipulation. So how you think that research that you're doing can contribute to some extent to something which has impact on industry, like food industry or agriculture industry?
I mean, I think, speaking to, for example, Lewis' talk, he said somewhere that this is mainly a system integration challenge. There wasn't, like, the challenge was mainly there. And hearing what Robert is saying, I am also getting the same feeling that if you narrow down the set of tasks that you want to do enough, you can, I guess what they're saying is that, you can take these existing tools and apply them to at least a narrow set of tasks in these domains. And those tools may be enough, but still there is the, turning it into a product challenge, which is huge. But it is it has always been the question in the back of my mind as well. Like, do we still need some fundamental algorithms or some fundamental hardware developments, fundamental scientific technical breakthroughs that that are necessary for agricultural or food manipulation, or is it just an engineering problem? But what I'm hearing is that maybe we are there. Maybe we can start if we simplify the tasks enough, I guess that is the feeling I'm getting. But I don't know if Lewis or Robert.
Yeah, I'm sorry, I was making it too focused on the product just to respond to this, but there is really this one key challenge when I'm thinking of taking something out of a container. If you look at a mess, and Mehmet, you might know this much better than I could describe it in some ways. Like if a human takes a spoon in their hands and you give them any containment of food in front of them, you can give them the task of give me about 100 grams of this food without using a scale. And they will somewhat succeed without their prior knowledge. They will be able to roughly give you 100 grams of that food. And you don't need a scale for this. All they do is their hands, their visual inputs, and some idea about, they don't even touch the food, but they know how heavy it is, right? And so now putting all of this like proprioception and that reasoning about the world into a robotic system to do the same thing, and then at the same time doing all this post-processing afterwards where you trying to get the stuff off the spoon afterwards. Like you go into the container and there's a little bit of mango still on it afterwards, and the human just does a short like whip on the side of the plate and it's gone. Like doing all of this in a robotic system, that's still research. And so you're trying to make your system as constrained as possible that you don't have to do any of those additional things. So the more you can do this, the more you make the system robust. At the same time, as a product, you're trying to solve it by making the system more constrained or using a disher, for example. Like we use a disher that takes care of this, right? So you have a metal thing that runs around and just that gets rid of the mango.
Yeah, I think I'll mention my perspective on this. I think in order to take something from the lab to production, this is not like an interesting take, but you just have to do the work. It's just a lot of work to bring it through that transition. So if I'm considering using something, some tool or framework or something like that, I'll look at who else has used it in production. And if I can't find anyone who's used it in production, then I know that I'll probably have to do a lot of work to make it production ready. So you just have to go into that with open eyes. And when we look at solving the problem at a high level, we have to understand like which aspects of these are just like systems level engineering problems, where we have a bunch of production ready components, we just have to integrate them together, versus where do I have to take state of the art research and make it production ready, which almost means like kind of implementing it from scratch with inspiration from this research. And then I have to know like what areas do I have to solve like new challenges from scratch. So like TrapTIG has certainly solved some problems like from scratch, like very very tricky problems in certain areas, and then we've taken some algorithms and brought them to production, and then we've done a lot of systems level work with like tools that were already quite robust. So you just have to kind of understand like where you are in each area. And then, like some of you have mentioned, just try to be as clever as you can about, constraining the problem or like, alleviating some of your constraints in a way that makes your, that really reduces the amount of overall work you have to do so that you can make it tractable.
Can I ask something to Lewis about, because you mentioned like using, let's say, third-party solutions, like things that come maybe from academia, and how much do you have a challenge of software integration? Because that's something we have been working on a bit in my team. So like, let's say, you mentioned using ROS, I think, so how much can you actually find? Have you bumped into things that you find the algorithms that you can directly put in your pipeline? Or
yeah, so the software integration is super tricky. When it comes to like ROS packages, I mean, we found that the core ROS tools are like pretty reliable, but when you look at like all the ROS packages that are available, it's all over the place, and it can be very tempting to like, when we encounter some problem, we go looking for existing solutions, and we'll find some that like seem perfect for us. And it's like, oh, this has all these like magical features, and it totally solves our problem. And it can be very tempting to just like put it into our code base and start using it. But we really have to like critically examine the components to see if they're ready for it, and if they're not quite ready, to try to understand like how much work we'll have to do to make it work for us. And
is it like exactly that process of testing things out? Is it something that you have the time to do? Like or you have the temptation of saying, okay, we can't really do it because it's too time consuming to test things out and understand whether they are right or not, so forget about it.
Do you have the time to do it? I mean, we try to take the best and quickest solution to every problem we encounter. And so if there's like a simpler solution, we'll do that. Sometimes we have to do the work. So sometimes we do, sometimes we don't.
I mean, might be also a question for secrets to success is like, when you take real-time robotics solution for motion planning, that was something we've looked into as well, versus doing some of those things just from ourselves or using other accessible resources. And in the end of the day, it's a question of how did you write your software stack in the first place? Did you even use ROS? Like, we didn't use ROS, we used something else. And so then, or can you use this proprietary solution, plug it into your code base and still rely on it and be sure your robot's not going to kill someone? That's also a difficult question. So it becomes a question of safety and how much can you trust the other company that they are allowed to run a motion plan on your robot. So, or then, like, we worked with a Franka arm, and Franka had a couple of restrictions on their end of what you're allowed to do with it and not, and how deep can you go into their codes and how much can you rely on their controllers. We end up writing our own controllers because we couldn't, right? So in the end of the day, I feel like a lot of these pieces, like building agriculture or any other products, kind of rely having a lot of intermediate products proven out in the market, like real-time robotics, like good grippers, good sensors, having all these things like already in the markets and having multiple players that already have kind of killed each other a little bit or played with each other. That makes these highly integrative problems easier. And we are not quite there yet, I would say.
So a more modular approach to the business of this is needed, you're saying?
Yeah, exactly. Like, there's a lot of value add by companies just solving a sub piece, like real-time robotics is doing it. I'm saying I think they're doing a right problem there, and many others are. And then companies that really want to put a solution out there that helps humankind to solve the food problem, they will then greatly benefit from these basic solutions and being able to put them together. The interfaces is the other problem, right?
Well, it's a chicken and egg problem, right? Why would the basic component companies build that if there's no customer for it? Is the question there, right? So yeah, but you're very right, yeah.
I mean, I ended up spending a lot of time just building this human obstacle avoidance and human detection solution because we didn't have something you could just buy for it, right? So you could in the end say, hey, should we have started a second company on the side that's now going to sell this solution to other companies because they might have a need for it? So, well, there's not enough money and the VC is not interested in paying that part. You have to go extra fundraise for this, right?
So Robert and Luis, now we have Lorenzo here. He's working on tactile sensor development. And in manipulation, we know human is benefiting a lot from this kind of sensing modalities. For real-time adaptation or real-time, let's say, controlling. To what extent do you think, because nowadays we don't probably have that sophisticated sensing modalities as human has in terms of the distribution across different point of the, let's say, hands. Do you think this is the kind of bottleneck that stops us to go further in terms of the manipulation capabilities that we have? Or is it algorithmic, let's say, side of the robotics that we need to push it forward? Or what is limiting us to get to the level of human capability for agri-food manipulation? This is a question to all of you, including Mehmet.
You're asking body and brain, right? Is it the body or is it the brain? Yeah.
Yeah.
I would say that my initial reaction is that right now the sensing is more limited than the algorithms. So, we know that when people go out and pick strawberries and other fruit, they use their touch feedback quite a bit. So they can like look at a plant and then look away and kind of go pick some of the right berries. And you know, so Traptic doesn't really use any like touch feedback or anything like that. You know, we looked at it and we decided it would be too difficult to make it like robust and food safe and have consistent results in this tough environment over a long period of time. So we said, okay, we're going to basically go cameras only, more or less. And like sometimes we play this game where we try to like be the robot. Like we'll like fix our fingers like this, like our gripper is, or we'll even hold a pair of pliers and we'll be like, okay, you can like look at the scene and then, you know, you take a picture and you close your eyes and you try to like go pick the stem. And it's like very hard to do, very hard to do it accurately. But that's like what we're trying to make our robot do. You know, whereas, you know, if we had that touch feedback, it would be a lot easier. So it does kind of seem to me like the sensing is currently more limited than the algorithms.
Do you know, Louis, do you know of these experiments where they have numbed humans' hands and then they try to give them spoons and do fine manipulation? And it always like give you a spoon, feed yourself, you know, it fails utterly. Even though you have gross motor experience, like you can still like move yourself around and everything, but really you're missing the final touch, right?
Yeah.
And I would say we humans are really good at manipulation, but we like once we lose this little bit of touch, it's like the end.
There are interesting videos about light matching with anesthetized fingertips, and it's not impossible, but very, very hard and almost impossible. Yeah.
Louis, we also tried to do this just with vision first. So like just try to get the right amounts. And it's just, I mean, let me ask you this. How much are you doing like complete closed loop control in your process versus, like that was one of the things that I find very hard because it's a very discrete action. You're trying to go and get a scoop and then you realize it was too little. So, but they already done with scooping at that moment. And when you go pick, right? So the moment you pick, the moment you start executing, you always have to then restart everything over again. And so this closed loopness in all of this process is such a challenging portion of the solution, right?
Yeah, I'd say ours is fairly open loop. You know, when we go pick a berry, we disturb the scene quite a bit. So, you know, you can't really like look at it afterwards and even know what you just did. You know, you look at the scene, you go try to grab, and then the scene looks totally different afterwards. You also, it's also hard for us to like see what we're doing as we're doing it, because when we, you know, if this is the berry, when we go up to grab it, our cameras get occluded when we arrive. So we can't necessarily see like what the gripper's doing. We can't see where it actually got to. We also have this like really high frame rate camera on the bottom of our gripper that we use to like record kind of debug video of the whole pick, so that our engineers can like look at it afterwards and understand like what it did each time. And yeah, that one's not necessarily calibrated with the like really high accuracy 3D cameras we're using. So even if you can see where the gripper tips ended up, it's kind of hard to correlate that with the original image you used to pick that. It's very tricky.
Yeah. Louis, have you seen the work from Lucas Manueli at Russ Tetrex Group? It's called Key Points into the Future. I think you would greatly benefit from this because it would allow you to do it in closed loop, what you're doing right now. If you use they use an autoencoder approach to close the loop. So
interesting. I'll have to check that out.
But like the key is they can basically close the loop continuously on running MPC on a trajectory, but they're feeding in key points of the object, which is very nicely done in an agricultural setting like yours, where you have crops, which are nicely to distinguish. And so they can adjust the single trajectory that you're planning for on the fly continuously by having this like dense, they call it dense object nets. It uses a dense correspondence architecture. You might have heard of it, I don't know, but I think it could be very valuable for your problem.
That's a great idea. I'll definitely check that out. Thanks.
So now, Mehmet, the question is that if we don't have yet that rich sensing modalities, is it wise to push forward the algorithmic development for motion planning, for clutter manipulation, or we need to wait or assume that we have to sensing modalities and then do clutter manipulation?
I mean, yeah, I guess what you're saying is, as we are manipulating, if we cannot see what is going on with vision, then we can't do closed loop. And then doing open loop with such a complex system is bound to fail unless, you know, you have very simplified instances of your problem. So yeah, I think that is the challenge we have, and I agree with Lorenzo in that. Like, you know, I think that is why we need tactile feedback. That, you know, when your camera isn't able to see anything, you know, you get the feedback. So that is that is definitely important, I think, and that is probably part of the reason why we don't have these systems working robustly yet. Yeah, I agree with that.
I do want to mention, you know, I would love to have that like kind of sensor feedback, especially if it was like very cheap. But like, I don't think we should necessarily like give up on solving it using algorithms. I mean, when you look at like when like early airplanes were developed, like at first everyone tried to do it like the way birds worked and tried to like make their wings flap and stuff. And then we ended up, what actually worked was like kind of a fairly different approach, you know, some similar aerodynamics concepts, but like kind of a different end solution. And so it could be the case that robotics will be the same thing. You know, maybe certain types of sensors will be harder and the algorithms, you know, maybe the sensors won't be as good and the algorithms will be way better than human. And maybe that will just work out.
Yeah, I think it's always a co-development anyway. So there's no such a thing as like stopping the software because we need better hardware, right? It's always going to be a co-development. Then it might be a bit unequal at times, but I think it's important probably for the, let's say, development of the use of tactile sensing in robotics. Is important that let's say to have works even with the, let's say, limited somehow sensors that we have at the moment, but starting using them so that we understand the problems and can then improve the sensor, so on. So it's a loop, right?
Lorenzo, we know that both the actuation mechanism and also the sensing modalities in human being are quite redundant. So we have a lot of redundancies in sensing modalities and actuations. So do we have a good understanding what is the minimal, let's say, sensing capabilities that is good to contribute to, let's say, 90% of the success? So how we can identify that and then work on that, which is probably not that much sophisticated, but it still gives us the majority of capabilities that we need. And then how far, first question, do we know this level of capability? Second question, if we know this capability, how far we are in terms of the technology from that level?
Yeah, no, I don't think we know. I mean, I don't. I don't know. I don't think we do. And I think what drives then is the applications, right? You see what you can achieve, what you cannot achieve. I don't know. In manipulation, we have robotic hands with 25 degrees of freedom since more than 30 years. Recently, there is more and more work in under-actuated mechanism, and we went definitely more using grippers and 1 degree of freedom hands, exactly because we saw that probably there were a lot of things we could do. I still think researching using multi-finger hands is interesting to push that and to see what is that we can actually achieve that we cannot achieve in other cases. I don't think there is really a limit because, as you say, if we look at humans, we are so redundant and we have so many more actuators and sensors than we could ever have in robots. So, yeah.
And Robert and Luis, thanks, Lorenzo. Robert and Luis, we know that for a specific application, for example, selective harvesting, we know the market, we know the requirements, and why not to design, like remove all the redundancies of human hands and then just focus on the very customized solution, as you did for your strawberry picking and for this kitchen robots that you did. Is it a good, in terms of the business perspective, is it a good approach to just customize the robotic solution, which is supposed to be scalable? And the difference, the main difference between the robotizing an industry and kind of mechanizing it is that we are adding more flexibilities and scalability. So do you think it is a good model in terms of the business service and business model, or we need to develop anyway that level of scalability so that the business is profitable at the end of the day?
Louis, if I have to actually go very quick, my 5 cents is this: the voice of the customer is always the one that determines it in the end. If the customer says, I'm happy with this sort of like minimized system that you provide to me, then yes, the answer is yes to what you said, that you can really simplify it down to the point that the customer is still happy with what it gets from it. And at least that's what we were trying to do, like cut all the slack and all the nice fanciness about the thing, and it's in the end not very exciting from a robotics perspective, but it's exciting to the customer because it just solves that one problem they have.
Thanks, Robert. I guess we will
finish Robert.
In 1 minute. Thank you very much.
Yeah.
Thank you.
Thanks, Robert.
Thank
and
you.
My take on that is that you're kind of asking about the question of do you use something off the shelf versus do you build a custom thing for your specific needs? And that's always a really hard question to answer in any like engineering organization, and even like I think in research contexts. During Traptic's history, we've really tried to use as much off-the-shelf stuff as we can. Because especially as a startup, you need to get to market very quickly, and anytime you can use an off-the-shelf thing, you speed yourself up quite a bit. So we've used as much off-the-shelf stuff as we can. But in many cases, we realize that the off-the-shelf stuff isn't working well, and so we develop our own custom stuff. So like we're using off-the-shelf robot arms, and we think those are great. We tried to use off-the-shelf 3D cameras for a long time, and then ultimately decided to build our own custom color stereo cameras. And I would not have guessed early on that that would have been the right thing to do, but in hindsight, I think it was. In terms of the gripper, we could have bought some of the, there's lots of gripper options available. We could have bought one of those and put it on there, but we ultimately decided to develop our own. And so the simple and boring answer is you kind of make the right decision given all of your, preferences and constraints. And so, for us, we had to do custom stuff. But if the off-the-shelf stuff, the better the off-the-shelf stuff is, the more often people will use that instead of building their own custom stuff. So, if we can make it really reliable and cheap and delicate and reliable and all that stuff, then people will use it more, and that's good for everyone.
Louis, how long have you been developing this system?
We've been working on this for 4 to 5 years now.
And can I ask how big your team is?
About 15 people.
15, okay. Cool.
So of the 15 people have worked on this product for 5 years. Okay.
We started off, the first year is just my co-founder and I. So the team has probably grown pretty constantly throughout that time.
Okay. Thank you, Luis. Thank you, Lorenzo. And thank you, Mehmet. Saria, over to you for best paper award.
Can I add a last point?
Go ahead.
I believe that benchmarking technologies is very helpful and easy the process for the people who work in the field and in the lab. And one of that cases is the case that Louis has presented in picking in cluster. And we saw, compare this case to the case, for example, that Mehmet works on, which is picking an object on a surface from a cluster. Comparing those together, we saw that the difference will be that the case scenario of the agriculture has the stems between them, between the elements suspended. So some of the researchers, in order to solve that question, decide to pick the fruit from cluster by pushing the fruit So they pick the fruit, they don't pick the stem. However, in Traptic, you show us that you pick from the stem, not the fruit. And this will remove us from working on the algorithm or developing algorithm to push obstacles away and to pick the right fruit, which is very helpful. And the reasoning behind this can be that stems are away from each other. So maybe it's easier to pick a stem and not a fruit and not go and push a fruit. And comparing this to the case of maybe Mahmoud, objects that are on the surface where there is no connections between them, you have a bit of space between them. So it's easier, it's not easier, it's the case that you go and push the objects to reach a goal. However, in 3D suspended case, is it easier to pick a stem than a fruit, than pushing a fruit and picking a fruit? So this is, I think this is a case of benchmarking, and I think benchmarking technologies can easy the research of many people. I think so.
Yeah, it definitely would be. It definitely like super helpful to understand like how good different things are, and when we're evaluating different approaches, it can be like very challenging to know how good each option is. I mean, you can look at the paper that each group published, but obviously people try to paint their own algorithms in a positive light. So having like some kind of more objective evaluation of them all is really useful. I also think that like, when we made the decision to switch from, grabbing the berry itself to grabbing the stem, part of the motivation is that we thought it was going to be challenging to move the other berries out of the way and in order to get to the target berry we want. So we were concerned that if we went and tried to find an off-the-shelf algorithm to do that, it would end up being a lot of work to integrate it. But there were other considerations. So the patented gripper we developed is like really good at grabbing soft objects like firmly but delicately, but it's also a very heavy gripper and it's kind of slow. So when we switched to our stem gripper, we had a very light gripper that's super fast and it's like super reliable, super cheap. So there are a lot of benefits there, and so that really motivated us to consider switching to that. So we kind of, we look at all the factors and we try to make the best decision for our needs. And I think if you have really reliable benchmarking, that helps you make much better decisions. And yeah, that's.
As a side note, let me throw in that we are organizing a benchmark on benchmarking for manipulation together with Maximo Roa and others at IROS 2000 this year. So stay tuned and get in touch.
Thank you.
Cool.
Thank you. So now, if I can maybe share my screen for announcing who the best 3 contributions that were made. Are you able to see my screen?
Yes. Yep.
Okay, so thanks for the contributors to the workshop, and the contributions that were awarded for this workshop were, the first one is learning to pick apples using an apple proxy from Oregon State University and authored primarily by Alejandro Velasquez. The second prize is the paper on execution monitoring for robotic pruning using force feedback, also contributed by Oregon State University and authored primarily by Alexander Yu. And the third one is the end-to-end deep learning stereo matching method for robotic leaf sampling from the University of Zhejiang, if I pronounced it well, and authored primarily by Qingyu Wang or Mingxuan Zhu, because there was an asterisk next to the second name. So thanks for the contributors, and we will get back in touch with you after the event. I will stop now sharing my screen. Yeah. And thank you for all the attendees and for all the talks and insightful talks really that we have reached. And thank you for being here and joining us.
Thank you, Saria, for organizing. Thomas, Amir, thank you very much.
Yeah, thank
thanks
you
for
for the
organizing.
interesting
It's
work.
awesome.
Thank you for the talks.
Have a
Thanks
good
for
day. Thanks.
have a good day.
Have a good day.
Cheers. Bye bye.
Cheers. Bye, everyone.